Lesson 1. Matter and Measurement. Welcome. Settle in, take a slow, deep breath, and let your mind relax as we begin a remarkable journey together into the very fabric of our universe. Close your eyes and allow the worries of the day to slowly drift away, replaced by a quiet sense of wonder. In this first lesson, we lay the groundwork together, exploring the fundamental nature of everything around us and the language we use to describe it. Before we can understand the complex, magnificent chemical reactions that power the stars or the delicate biology of our own bodies, we must first learn how to simply observe and quantify our surroundings. We are starting at the very beginning. We are going to learn how to look at the world with the patient, precise eyes of a scientist. So, as you rest, let us take this first, gentle step together and explore the clay from which the cosmos is sculpted. Everything you can see, touch, or breathe is made of matter. Simply put, matter is anything that has mass and takes up physical space. It is the substance of reality. Think of it as the foundational material of existence. This material comes in three primary states that you already know intimately from your everyday life. First, consider the solid state. When matter is in a solid form, its constituent parts are held closely and tightly in a fixed, rigid arrangement. Imagine the quiet strength of a grand oak tree, the cool, smooth surface of a stone resting on a quiet beach, or the comfortable bed you are lying in right now. The particles within these solid objects are locked in a steady embrace, giving the object a definite shape and a definite volume. They do not bend to the will of their container, they hold their ground. Next, we have the liquid state. In a liquid, the particles are still touching, but they are no longer locked in place. They have the freedom to slide past one another, gracefully and fluidly. Because of this freedom, a liquid has a definite volume, but it does not have a definite shape. It flows gently to perfectly fill whatever container holds it. Picture a cool glass of water, or a quiet river meandering through a sleepy valley. The liquid yields and adapts, resting perfectly in the space it is given. Finally, we have the gaseous state. In a gas, the particles have been given total freedom. They are separated by vast, empty distances, constantly flying and bouncing in every direction. A gas has neither a definite shape nor a definite volume. It will expand endlessly to fill any container it is placed within. Think of the unseen air filling the room around you, bringing you oxygen with every breath you take. It is expansive, weightless, and entirely free. To understand this matter, whether it is a heavy stone, a flowing river, or the invisible air, we must measure it. Measurement is how we ask nature questions and listen to her answers. In chemistry, we use a beautifully logical system called the metric system, specifically the International System of Units. Unlike older systems of measurement that relied on arbitrary things like the length of a king's foot, the metric system is grounded in the universal constants of nature, and everything scales perfectly by tens. We measure length in meters, mass in kilograms, time in seconds, and temperature in Kelvin. By simply adding prefixes like kilo for 1,000 or milli for 1,000th, we can seamlessly climb up and down the scale of the universe, from the mass of an entire planet to the width of a single, microscopic human hair, all using the exact same harmonious language. When scientists measure the world, they care deeply about two distinct concepts: accuracy and precision. We often use these words interchangeably in casual conversation, but in the quiet discipline of a laboratory, they mean two very different things. Accuracy is a measure of how close we are to the true, objective value of something. Imagine a target on a wall, with a red bullseye dead in the center. If you throw a dart and it lands right in that red circle, your throw was accurate. Precision, on the other hand, is a measure of how consistently we can repeat a measurement, regardless of whether it is correct. Imagine throwing 3 darts. If all 3 darts land tightly clustered together in the upper corner of the board, far away from the center, your throws were highly precise, but not accurate. The goal of every careful scientist is to be both accurate and precise, to hit the center of the truth over and over again. This brings us to a beautiful and humbling concept in chemistry: uncertainty. No matter how expensive or advanced our measuring tools are, every measurement we ever make has a tiny bit of uncertainty built into it. A scale might tell you a gold coin weighs 12.5 grams, but what lies beyond that decimal? Is it 12.51? 12.50? We can never know with absolute, infinite certainty. Because of this, chemists use a system called significant figures. Significant figures are a way of being completely honest about what we know and what we do not know. When a scientist writes down a number, the number of digits they use tells you exactly how confident they are in their tool. We never pretend to have more precision than our instruments actually allow. It is a system built entirely on intellectual honesty and humility in the face of nature's vastness. Centuries ago, early alchemists struggled deeply without a unified system of measurement or this shared honesty. A recipe from an apothecary in one city could not be reliably recreated in another because a handful or a pinch meant something entirely different to every person. It wasn't until the late 18th century, during the quiet dawn of the modern scientific revolution, that the metric system gave the world a shared, precise language. For the first time in human history, scientists across the globe could whisper their discoveries to one another in a common tongue, allowing our collective understanding of the universe to truly blossom. So you see, this careful attention to matter and measurement is not just an abstract theory kept in a dusty textbook. It is the invisible anchor of our modern reality. It is the principle that explains why a massive steel suspension bridge holds firm under the weight of thousands of cars, because the engineers measured the mass and forces with perfect, unyielding precision. It is the reason a baker's precisely measured ingredients rise in the oven into a perfectly soft, warm loaf of bread, rather than falling flat. More importantly, it is the reason a doctor can prescribe a life-saving medication, knowing that the exact milligram dosage will gently heal the body without overwhelming it. Measurement bridges the vast gap between the abstract ideas in our minds and the physical, tangible universe we inhabit. It is how we make the world safe, predictable, and understood. Having grounded ourselves in the language of measurement and the broad, sweeping concepts of solid, liquid, and gas, we are perfectly prepared to look a little closer. We have looked at the whole tree, now we must look at the leaves. Let this foundational knowledge settle quietly into your memory, a sturdy floor upon which we will build everything else. When we transition into our next lesson, we will dive deep into the microscopic, invisible building blocks that make up all the matter we have just learned to measure. We will meet the atom. Lesson 2: Atoms, Molecules, and Ions. Welcome back. As you lie here, comfortable and still, let your mind return to the quiet, focused space we created together. In our last session, we looked at the grand, sweeping forms of matter, the solid ground beneath us, the flowing rivers, and the expansive, unseen air. We learned how to measure these bulk materials with precision, assigning numbers to their weight and volume. Now, we are going to take a journey inward. We are going to gently close our eyes and zoom in, far beyond what any human eye or traditional microscope can ever hope to see. We are going to explore the invisible, foundational pieces of our world. Just as a grand, sweeping novel is ultimately composed of individual letters, all the matter we observe is built from tiny, indivisible characters. Tonight, we will meet them. We will take the next natural step in our journey, discovering how the vast complexity of the universe is built from just a few simple, elegant building blocks. Imagine, in your mind's eye, taking a solid piece of pure, gleaming gold. Now, imagine cutting that piece of gold perfectly in half. Then, take one of those halves and cut it in half again. If you were to continue this process patiently, over and over, you would eventually reach a point where you are holding a piece of gold so infinitesimally small that it can no longer be physically divided. If you somehow managed to cut it again, it would shatter its identity and cease to be gold at all. That ultimate, indivisible speck is the atom. The atom is the fundamental unit of all chemical elements. But the atom is not just a solid, uniform little sphere. It has a magnificent, tiny anatomy of its own. Deep within the very center of the atom lies the nucleus. The nucleus is incredibly small compared to the whole, yet it contains almost all of the atom's mass. It is a dense, heavy core made of two types of particles packed tightly together. The first are protons, which carry a strong positive electrical charge. The second are neutrons, which carry no charge at all. They are entirely neutral, acting as a quiet buffer that helps hold the positively charged protons together. Swirling around this heavy center, in the vast empty spaces of the atom, are the electrons. Electrons are wonderfully strange, remarkably light, and incredibly nimble particles that carry a negative electrical charge. Because opposite charges attract one another in nature, the negative electrons feel a constant magnetic pull toward the positive nucleus. This beautiful, balanced tension is what keeps the atom whole and intact. Much like distant planets are held in orbit by the gravitational pull of a quiet sun. When two or more of these atoms reach out and hold on to one another, they form what we call a molecule. A molecule can be a simple pair of the exact same atoms, like the oxygen you are breathing right now, or it can be a beautiful, intricate mosaic of many different types of atoms working together. However, sometimes in the energetic dance of chemistry, an atom might lose one of its quick-moving electrons, or it might steal an extra one from a neighboring atom. When this happens, the perfect balance of positive protons and negative electrons is upset. The atom gains a net electrical charge, and its name changes. We call this charged particle an ion. If an atom loses a negative electron, the positive protons outnumber the negatives, and it becomes a positively charged ion, known as a cation. If it gains an extra electron, it becomes a negatively charged ion, known as an anion. These charged ions are the restless, invisible forces that drive so much of the movement and reaction in our physical world. The story of discovering the atom is one of the greatest mysteries humanity has ever unraveled, requiring immense patience and imagination. The very word atom comes from the ancient Greek word atomos, which simply translates to indivisible. Thousands of years ago, early philosophers sat under the stars and deduced through pure logic that there must be a bottom floor to reality, a point where things could no longer be broken down. But it wasn't until the early 19th century that a quiet English schoolteacher named John Dalton brought this philosophical idea into the rigorous light of modern science. Dalton proposed that each element is made of its own unique, identical atoms, and that chemical reactions are simply the rearranging of these indestructible pieces. Many decades later, a brilliant physicist named Ernest Rutherford conducted an elegant experiment that changed our understanding of reality forever. He took a whisper-thin sheet of gold foil and shot tiny, positively charged particles at it, fully expecting them to punch right through the atoms like bullets passing through tissue paper. But to his absolute astonishment, a few of the particles bounced straight back toward him. He realized they had hit something incredibly dense and heavy hidden in the center. He had discovered the nucleus. Rutherford's beautiful discovery revealed a truth about our universe that is almost too profound to easily grasp. The atom is overwhelmingly composed of empty space. To understand this scale, imagine enlarging a single atom so that its nucleus was the size of a small glass marble, sitting exactly on the 50-yard line of a massive football stadium. In this giant atom, the nearest electrons would be tiny gnats buzzing frantically all the way up in the highest, furthest bleachers. Everything in between the marble and the gnats is just vast, empty space. This means the solid bed you are resting on, the walls holding up your room, and even your own physical body, they are composed almost entirely of nothingness. The things around us only feel solid because the swirling, buzzing negative electron clouds of the atoms in your hand violently repel the negative electron clouds of the atoms in the objects you touch. Like two incredibly strong magnets pushing each other away before they ever make physical contact. This understanding of atoms, molecules, and ions is not just a parlor trick of physics. It is the master key to unlocking the secrets of the world you interact with every single day. Consider the simple, comforting sight of a glass of cool water resting on a nightstand. That water is not a single, continuous fluid. It is a vast, shimmering collection of billions upon trillions of specific molecules. Each individual water molecule is born from the gentle, specific union of two small hydrogen atoms and one slightly larger oxygen atom. Or consider the salt you might sprinkle on a warm meal. Table salt is entirely different from water. It is not made of independent, free-floating molecules. Instead, it is a massive, repeating, three-dimensional grid of sodium ions and chloride ions. The sodium atoms have each given up an electron, becoming positively charged cations, and the chlorine atoms have gladly accepted those electrons, becoming negatively charged anions. Because opposites attract so fiercely, they lock together in a perfect, rigid, crystalline embrace by the sheer force of their electrical charges. When you place a crystal of that salt on your tongue, the moisture in your mouth gently pulls those ions apart, and your taste buds recognize the sudden, sharp rush of those charged particles, translating that microscopic chemistry into the sensation of taste. From the salt on your table to the complex proteins quietly rebuilding your muscles as you rest, everything is simply a rearrangement of these fundamental pieces. Let us hold that thought right here, resting comfortably on this complete piece of the puzzle. You now know the central characters in the grand, ongoing story of chemistry. You have met the heavy, quiet protons and neutrons, the swift electrons, and the molecules they form when they join hands in the dark. But in order for these characters to interact, to react, and create all the materials of our universe, they must be brought together in very specific amounts. When we return in our next lesson, we will learn how to count these invisible particles and weigh them in chemical reactions, unlocking the elegant, balancing mathematics of stoichiometry. Sleep well, and let the quiet, spinning wonder of the atomic world accompany you into your dreams. Lesson 1. Matter. Lesson 3. Stoichiometry. Chemical calculations. Welcome back. Let your breathing settle into a slow, comfortable rhythm and allow the quiet of the room to gently surround you. In our previous moments together, we journeyed into the unimaginably small, discovering the atoms, ions, and molecules that serve as the fundamental building blocks of our universe. We marveled at their structure and their quiet, swirling energy, but simply knowing the pieces is only the beginning of understanding the puzzle. In this lesson, we take the next natural step together. We are going to learn how to read nature's recipes. We will explore the elegant, balancing mathematics of chemistry, learning how these tiny, invisible pieces combine and transform in perfect, highly predictable ratios. There is a deep, comforting order to the universe, and tonight we will learn how to measure it. The title of this lesson contains a word that often sounds intimidating to a new student: stoichiometry. It is a sharp, complex-sounding word, but I want you to strip away that intimidation. The word simply comes from two ancient Greek roots, stoichein, meaning element, and metron, meaning measure. Stoichiometry is nothing more than the gentle art of measuring elements. It is the accounting system of chemistry, and at its heart, it operates exactly like a recipe you might use in your own kitchen. Imagine you are standing in a warm, quiet kitchen, preparing to bake a batch of simple sugar cookies. Your recipe dictates that to make exactly 1 dozen cookies, you need 2 cups of flour, 1 cup of sugar, and 1 stick of butter. This ratio is absolute. If you invite more friends over and suddenly need to make 2 dozen cookies, you do not need to guess how much of each ingredient you need. You simply rely on the ratio. You double the flour to 4 cups, double the sugar to 2 cups, and double the butter to 2 sticks. Chemical equations work in this exact same, beautifully predictable way. When hydrogen gas and oxygen gas combine to form water, they always do so in the exact same proportion. But here, we face a profound challenge. You can easily use a measuring cup to scoop out flour, but how do you measure out atoms when they are too small to see, let alone pick up with your hands? We cannot simply count out 2 hydrogen atoms and 1 oxygen atom to make a single water molecule. The quantities are too impossibly small. To bridge this gap, chemists use a very special, profoundly important unit of measurement called the mole. When you hear the word mole in chemistry, do not think of the small, burrowing animal. Think of it purely as a counting word. In our everyday lives, we use counting words all the time. The word dozen always means exactly 12 of something. A dozen eggs is 12 eggs. A dozen roses is 12 roses. The word gross means 144. The mole operates in the exact same way. It is simply a word that stands for a specific number. Because atoms are so vanishingly small, the number of them required to make something you can actually hold in your hand is staggeringly large. Therefore, 1 mole equals a massive, almost incomprehensible number, 6.022 times 10 to the 23rd power. That is, a 6 followed by 23 zeros. If you had a mole of marbles, they would cover the entire surface of the Earth, several miles deep. But because atoms are so minuscule, a mole of water molecules, all those trillions upon trillions of particles, fits perfectly into a single, small sip of water resting at the bottom of a glass. The mole is our bridge. It allows us to group atoms into countable batches, turning the invisible world into something we can weigh on a scale. To truly appreciate the beauty of this chemical accounting, we must travel back to the late 18th century, to a quiet, dimly lit laboratory in Paris. Here, a brilliant and meticulous scientist named Antoine Lavoisier worked alongside his equally brilliant wife, Marie-Anne. Before Lavoisier, chemistry was still entangled with alchemy, and experiments were often chaotic. But Lavoisier brought strict, uncompromising measurement to the science. He would place chemicals inside carefully sealed glass vessels and weigh them on the finest, most precise brass scales in the world. He would then heat the vessels, causing the chemicals inside to react, change color, release smoke, and form entirely new substances. Yet, when he allowed the glass to cool and weighed the vessel again, the weight had not changed by a single fraction of a gram. Through this quiet, patient observation, Lavoisier proved the law of conservation of mass. This fundamental law of nature states that matter cannot be created, nor can it be destroyed, in a chemical reaction. The universe is a closed system. If you start a reaction with exactly 10 billion carbon atoms, you must finish that reaction with exactly 10 billion carbon atoms. They may have unclasped their hands from one type of molecule and reached out to form a completely different molecule, but the total number of atoms remains absolutely constant. They just change their costumes. This is why stoichiometry is so vital. It allows us to write chemical equations that honor Lavoisier's discovery. We use the mole to calculate the molar mass of every element, which is simply how many grams 1 mole of that specific element weighs. Carbon is relatively light, so 1 mole of carbon weighs about 12 grams. Lead is much denser, so 1 mole of lead weighs over 200 grams. By understanding these weights, a chemist can look at a balanced equation on a piece of paper, walk to a laboratory bench, and weigh out the exact, perfect amount of physical powders and liquids needed so that every single atom finds a partner, leaving absolutely nothing to waste. This perfect, balanced accounting is not merely an academic exercise meant for chalkboards and textbooks. It is a life-saving application of natural law. Consider the steering wheel of the car sitting quietly in your driveway. Inside that wheel is a folded airbag, and tucked inside that bag is a precise amount of a solid chemical called sodium azide. When a collision occurs, an electrical sensor triggers that solid powder to rapidly decompose into nitrogen gas, which inflates the bag in a fraction of a second to cushion the driver. How do the automotive engineers know exactly how much sodium azide to put in the steering wheel? They use stoichiometry. If they use too little, the bag will not inflate enough to provide a soft cushion. If they use too much powder, the reaction will generate too much gas, and the bag will violently burst. By using the mole, they can calculate the exact mass of solid required to produce the precise volume of gas needed to safely cradle a human life. It is the math of protection, grounded in the unyielding laws of mass and balance. We have now mastered the art of balancing nature's recipes on paper. We understand how to count the unseen and how to track the mass of the universe as it gently transforms from one substance to another. We have learned to read the sheet music of chemistry, but music must eventually be played. Having learned the theory, we are now ready to see these reactions in action. When we return, we will take these carefully measured solids, dissolve them into the quiet embrace of water, and watch them interact in the vibrant, flowing world of solutions. Rest now, knowing the universe is perfectly balanced and nothing is ever truly lost. Lesson 1. Matter. Lesson 4. Aqueous reactions and solution stoichiometry. Welcome back. In our previous moments together, we learned how to read the fundamental recipes of nature. We learned to count invisible atoms using the mole, and we explored the elegant, balancing mathematics of stoichiometry. But until now, we have mostly imagined these chemicals as dry, resting powders or floating, isolated gases. In truth, the most profound and beautiful chemistry in our universe rarely happens in a dry, empty space. In this lesson, we take those dry ingredients and introduce them to the most vital, life-giving substance on Earth. We are moving from the dry chalkboard to the fluid, dynamic environment of water. We are going to explore the reactions that take place in aqueous, or water-based, solutions, watching how the rigid rules of math soften and flow in a liquid world. To understand an aqueous reaction, we must first deeply understand the environment where it takes place, water itself. Water is frequently called the universal solvent, a title it has earned through its unique, beautiful molecular shape. Imagine a single water molecule. It is composed of one large oxygen atom and two smaller hydrogen atoms, but they are not arranged in a straight, rigid line. Instead, the hydrogen atoms sit at an angle, making the molecule look a bit like a tiny boomerang or a resting butterfly with raised wings. Because of this bent shape, and because oxygen is inherently greedy for electrons, the oxygen end of the molecule holds a slight negative electrical charge, while the hydrogen ends hold a slight positive charge. This means every single water molecule is like a microscopic, gentle magnet, with a positive pole and a negative pole. We call this property polarity. Now, imagine taking a rigid, crystalline grain of table salt, a tightly bound grid of positive sodium ions and negative chloride ions, and dropping it into a glass of pure water. Instantly, a microscopic dance begins. The water molecules crowd around the salt crystal. The negative oxygen ends of the water molecules are magnetically drawn to the positive sodium ions on the surface of the crystal. At the same time, The positive hydrogen ends of the water molecules reach out and gently pull on the negative chloride ions. Through this constant, gentle, magnetic tug-of-war, the water molecules slowly pull the salt crystal completely apart, piece by piece. As each ion is pulled away from the solid structure, it becomes entirely surrounded by a spherical escort of water molecules. We call this protective escort a hydration shell. The ion is now floating freely, comfortably suspended in the liquid. The solid has completely dissolved. We call this uniform, perfectly mixed liquid a solution. The water is the solvent doing the dissolving, and the salt is the solute, the substance being dissolved. But the true magic happens when we bring two different solutions together. Imagine pouring a clear, colorless, aqueous solution of silver nitrate into a beaker containing a clear, colorless solution of sodium chloride. The moment the two liquids mix, the billions of freely floating ions are suddenly introduced to one another. Most of them will drift past each other without a second thought. But occasionally, a free-floating silver ion will brush past a free-floating chloride ion. These two particular ions have an incredibly strong magnetic attraction to each other, an attraction far stronger than the gentle pull of the water molecules surrounding them. The moment they touch, they lock together in an unbreakable embrace, instantly forming a heavy, solid particle that the water can no longer hold. As millions of these pairs find each other in a fraction of a second, a cloudy, brilliant white solid suddenly materializes out of the clear liquid and gently drifts to the bottom of the beaker like a quiet snowfall. We call this beautiful phenomenon a precipitation reaction, and the soft solid that forms is the precipitate. It looks like magic, creating a solid out of thin air, but it is simply the natural consequence of ions finding their perfect chemical match. Not all substances behave the same way in the embrace of water, and this brings us to the concept of electrolytes. An electrolyte is simply a substance that, when dissolved in water, allows the liquid to conduct electricity. When you dissolve salt in water, as we just visualized, it breaks apart completely into charged ions. These free-flowing charges act like an invisible electrical highway, allowing a current to pass through the water effortlessly. We call this a strong electrolyte. However, if you stir a spoonful of sugar into that same glass of water, a very different process occurs. The water molecules still surround the sugar molecules and pull them away from the crystal, dissolving them perfectly. But the sugar molecules do not break apart into charged ions. They remain whole, neutral molecules floating in the water. Because there are no free-flowing charges, the sugar water cannot conduct electricity at all. It is a non-electrolyte. Understanding this hidden electrical capacity is crucial to understanding how energy moves through liquid systems. Furthermore, we must address how chemists perform their precise calculations, their stoichiometry in this fluid environment. You cannot easily place a handful of dissolved ions on a brass scale to weigh them. Instead, chemists measure the amount of a chemical in a solution by its concentration. The most common way we measure this is a beautiful, standard unit called molarity. Molarity is simply a count of how many moles of a solute are swimming inside exactly 1 liter of the total solution. Think of it like describing the steepness of a cup of tea. If you put 1 tea bag in a large pot of water, the concentration is very low, the flavor is weak, and the molecules are spread far apart. If you put 1 tea bag in a tiny teacup, the concentration, the molarity, is very high. The flavor is robust, and the molecules are densely crowded together. By knowing the molarity of a solution and measuring the volume of liquid we pour into a beaker, we can calculate the exact number of invisible atoms we are delivering to the reaction, allowing us to maintain our perfect Lavoisian balance even in a splashing, shifting liquid. This understanding of aqueous chemistry is not confined to the glass beakers of a laboratory. It is the fundamental chemistry of the natural world. Look out at the vast, rolling oceans covering our planet. The ocean is not simply water, it is a massive, complex aqueous solution, rich with dissolved salts and minerals that govern the climate and sustain all marine life. Consider the quiet, ancient beauty of a limestone cave. Over thousands of years, water carrying dissolved minerals drips slowly from the cavern ceiling. As each drop hangs suspended in the dark, a microscopic precipitation reaction occurs, leaving behind a tiny, almost imperceptible ring of solid rock. Drop by drop, century by century, this delicate chemistry builds the massive hanging spires of stalactites. Most intimately, aqueous chemistry is the foundation of your own existence. The blood pulsing gently and rhythmically through your veins as you rest is an elaborate aqueous solution. It perfectly balances dissolved oxygen, vital nutrients, and essential electrolytes, carrying them silently to every cell in your body. Without the dissolving power of water, life itself would be entirely impossible. We have now watched molecules mix, dissolve, and react in the quiet, fluid depths of an aqueous solution. We have seen how water acts as the grand stage for chemical transformations. But every single one of these reactions, whether a solid falling like snow in a beaker or a fire burning brightly in a hearth, involves an invisible transfer of energy. Some reactions give off a deep, comforting warmth, while others draw heat away, leaving a cool chill in their wake. Having mastered the material changes of chemistry, we are now ready to explore the invisible forces that drive them. When we return, we will shift our focus to the glow of the fire, diving into the study of heat and energy in our next lesson on thermochemistry. Sleep peacefully and let the gentle, fluid nature of water carry you smoothly into your dreams. Lesson 1. Matter. Lesson 5. Thermochemistry. Welcome back to our shared space of quiet learning. Settle deeply into your surroundings, close your eyes, and let the gentle rhythm of your breathing guide you into a state of total relaxation. In our previous moments together, we watched as molecules mixed, dissolved, and rearranged themselves in the calm, fluid depths of aqueous solutions. We have mastered the physical movements of matter, tracking atoms as they gracefully change their partners. But in all of those interactions, we left out one invisible, vital ingredient. Now, we must turn our attention to the silent spark that drives all of nature's transformations. In this lesson, we will explore the flow of heat and energy. We are going to step into the world of thermochemistry, discovering the invisible warmth and the sudden chills that are born whenever matter reaches out to change its form. The word thermochemistry beautifully reveals its own meaning. It is the marriage of thermo, meaning heat, and chemistry, the study of matter. At its most fundamental level, thermochemistry asks a very simple question. Where does the heat in a fire actually come from, and where does it go? To answer this, we must fundamentally change how we visualize a chemical bond. In our earlier lessons, we imagined bonds as simple handshakes holding atoms together. Now, I want you to picture those bonds as invisible storage tanks of potential energy. Just like a boulder resting at the very edge of a high cliff has the potential to release a massive amount of energy if it falls, atoms holding onto one another hold a specific amount of stored, quiet energy. There is a common misconception that breaking a chemical bond releases energy, like snapping a taut rubber band, but nature actually works in the exact opposite way. To break a bond apart, to pull two perfectly content atoms away from each other, you must put energy into the system. You have to physically pull them apart against their will, much like pulling two strong magnets away from one another. It requires effort. It requires energy. Conversely, when two separate, free-floating atoms finally find each other and lock together into a new chemical bond, they are settling down into a more stable, comfortable state. And just as you might release a long, contented sigh when you finally sit down in a comfortable chair at the end of a long day, atoms release energy when they form a new bond. Every chemical reaction is simply a balance of these two events, old bonds breaking and new bonds forming. If a chemical reaction requires more energy to break the old bonds than it gives back when the new bonds form, the reaction has an energy deficit. It must steal heat from its environment to survive. When it pulls that heat away from your skin, the reaction feels cold to the touch. We call this an endothermic. Process energy moves inward. On the other hand, if a reaction requires only a tiny spark of energy to break the old bonds, but releases a massive cascading wave of energy when the beautifully stable new bonds form, there is leftover energy. That surplus energy radiates outward into the world as heat and light. When you hold your hands near this kind of reaction, you feel a deep, comforting warmth. We call this an exothermic. Process energy moves outward. It is the story of energy settling into its most comfortable resting place. To truly appreciate this invisible flow, we must look at one of the most profound and unbreakable rules of our universe, the first law of thermodynamics. This law, often called the law of conservation of energy, states a beautiful, poetic truth. It says that the total energy of the universe is absolutely constant. Energy cannot be created from nothing, and it can never, ever be destroyed. It simply changes its costume. The ancient chemical energy stored quietly for millions of years inside a lump of black coal is not destroyed when it is burned. It simply transforms into the radiant heat energy of a fire. That heat energy can be used to boil water, transforming into the kinetic energy of rising steam. The steam can spin a heavy iron turbine, transforming into mechanical energy, which then pushes electrons through a copper wire, transforming into electrical energy. Finally, that electrical energy travels into your home to power the soft glow of a reading lamp, returning the energy back into the room as light and warmth. Not a single fraction of a drop of energy was ever lost in that magnificent journey. It only shifted its form. In thermochemistry, we track these shifts using a concept called enthalpy. Enthalpy is simply a chemist's way of measuring the total heat content of a system at a constant pressure. We measure the change in enthalpy, watching carefully to see if the heat goes up or goes down as the reaction takes place. But how do we actually measure something as invisible and fleeting as heat? We use an elegant, brilliantly simple instrument called a calorimeter. Imagine a perfectly sealed, heavily insulated metal box. Inside this box is a small chamber where we place our chemical reaction. We surround that inner chamber with a perfectly measured pool of pure water, and we place a highly sensitive thermometer into the water. As the chemical reaction sparks and takes place inside the hidden chamber, it cannot share its heat with the outside room because of the heavy insulation. It can only share its heat with the surrounding water. By simply watching the temperature of the water gently rise or fall, we can calculate the exact, precise amount of energy that the molecules released or absorbed during their invisible dance. We capture the fleeting heat and translate it into permanent numbers. This grand law of energy conservation and the careful study of heat is what keeps human civilization turning. When you wake up on a crisp, freezing morning in the mountains and ignite a small camp stove to boil water for coffee, you are relying entirely on an exothermic reaction. The propane gas in the canister is eagerly reacting with the oxygen in the cold mountain air, snapping into incredibly stable new bonds and releasing their massive surplus of stored energy as a bright, hot blue flame to warm your hands. Conversely, if you ever twist an ankle on a hike and crack a plastic instant cold pack to soothe the swelling, you are holding a controlled endothermic reaction. Inside that plastic pouch, a solid salt is suddenly mixing with water. The process of pulling those salt crystals apart requires so much energy that it aggressively steals heat from the water, from the plastic pouch, and ultimately from your bruised skin, dropping the temperature dramatically in a matter of seconds. Even right now, as you rest quietly, your own body is a masterful, slow-burning furnace. You are slowly, carefully breaking down the food you ate today in a series of gentle exothermic reactions, releasing just enough heat to keep your core temperature perfectly maintained. You are a walking universe of thermodynamics. Having felt the warmth of chemical reactions, and having traced the beautiful, unbreakable laws of energy that govern our universe, we have completed a major chapter of our journey. We understand how matter moves, how it balances, and why it releases heat. Now, we must ask the deepest question yet. What is the actual physical nature of these bonds? What is the invisible glue holding this potential energy? To find the answer, we must look inward once again, diving past the nucleus, deep into the very architecture of the atom itself. Next, we will leave the heat behind and trace the mysterious, swirling paths of the electron in our lesson on the electronic structure of atoms. Sleep deeply and let the quiet, conserved energy of the universe keep you warm. Lesson 1. Matter. Lesson 6. Electronic structure of atoms. Welcome back. As we begin again, take a moment to simply be still. Let your shoulders drop, allow your breathing to slow, and feel the quiet comfort of the space around you. In our last session, we felt the warmth of chemical reactions, and we traced the beautiful, unbreakable laws of energy that govern our universe. We learned that energy is stored in the silent bonds holding atoms together. Now, we must ask a deeper question. What exactly forms those bonds? What is the physical substance of that connection? To find our answer, we must leave the macro world of heat and beakers behind and journey inward once again. We are going back to the atom, but this time we will look closer than we ever have before. In this lesson, we will explore the quiet, complex, and astonishingly beautiful dance of the electron, uncovering the electronic structure that gives matter its true identity. For a very long time, scientists pictured the atom in a way that was simple, clean, and comforting. They imagined the heavy, positive nucleus sitting perfectly still in the center, with the tiny negative electrons orbiting around it in perfect, flat, geometric circles. Much like planets orbiting a quiet sun, it is a beautiful image, and you have likely seen it drawn this way in textbooks or symbols of science. But as our instruments grew sharper and our minds reached further, we discovered that reality is far more mysterious and, frankly, far more beautiful. Electrons do not follow neat, predictable paths. They do not travel in perfect circles. In the microscopic realm of the atom, the rules of our everyday world simply melt away. Instead of planetary orbits, electrons live in what we call orbitals. An orbital is not a path. It is a three-dimensional cloud of probability. It is a region of space where an electron is most likely to be found. To visualize this, imagine walking through a quiet, dark forest on a warm summer evening and coming across a single porch light surrounded by a swarm of glowing fireflies. Because they are moving so incredibly fast, darting in every possible direction, you cannot predict exactly where one specific firefly will be at any given millisecond. Your eye cannot track a single path. But if you stand back and soften your gaze, you can clearly see the general shape of the entire swarm. You know where the fireflies are most likely to be clustered tightly near the warm light, thinning out as you move further into the dark trees. An electron behaves much like this swarm. Because it moves with such unimaginable speed, it smears out into a fuzzy, vibrating cloud of negative charge around the nucleus. We cannot know an electron's exact location and its exact speed, at the same time a profound truth known as the Heisenberg uncertainty principle. Nature, at its very foundation, holds on to a tiny bit of mystery. We can only map the shape of the cloud, the gentle, spherical, and lobed spaces where the electron spends its time. This shift from rigid planetary orbits to vibrating clouds of probability ushered in the era of quantum mechanics, a quiet revolution of thought that occurred in the 1920s. Two brilliant minds helped paint this new picture of reality: Niels Bohr and Erwin Schrödinger. Bohr offered us the concept of energy levels. He realized that electrons cannot just drift anywhere they please. They are restricted to very specific distances from the nucleus, like steps on a staircase. An electron can stand on the first step or the second step, but it can never float in the empty air between the steps. These steps are called energy levels, or shells. The closer a shell is to the positive nucleus, the more tightly held and comfortable the electron is. But it was Erwin Schrödinger who gave us the breathtaking shapes of these clouds. He discovered that electrons possess a dual personality. They act as solid, tiny particles, but they also ripple and flow as waves of pure energy, like the gentle ripples spreading across a quiet pond. By treating the electron as a wave, Schrödinger's complex mathematics revealed that the energy shells are divided into specific subshells, and each subshell has a unique, three-dimensional shape. The simplest of these is the s orbital, which is shaped like a perfect, soft sphere wrapped around the nucleus. As we move to higher energy levels, the shapes become more complex. The p orbitals look like softly glowing hourglasses or dumbbells, pointing in three different directions in space. Further still are the d and f orbitals, whose shapes bloom like incredibly complex, multi-petaled flowers unfolding in the dark. Every single electron in an atom has a specific, unique address within this beautiful architecture. They fill these shells and subshells one by one, always seeking the lowest, most comfortable resting place available, following strict cosmic rules. We call this complete map the atom's electron configuration. It is the ultimate blueprint of an element. The arrangement of those outermost electrons, the ones resting in the highest, furthest clouds, dictates exactly how that atom will interact with the rest of the universe. This seemingly abstract quantum architecture is responsible for all the light and color in our physical world. Remember Bohr's staircase. When an atom absorbs energy, perhaps from heat or electricity, an electron absorbs that energy and jumps violently up to a higher, less stable step. But it cannot stay there. Almost immediately, it falls back down to its comfortable resting cloud. As it drops, it must release the extra energy it had absorbed. It releases this energy as a single, perfect particle of light called a photon. The distance the electron falls dictates the exact color of the light. This is why a neon sign in a dark city window glows with such a brilliant, piercing red. Electricity is being pumped through a glass tube filled with neon gas, knocking the neon electrons up the staircase, and as they continuously fall back down to their specific resting places, they release that distinctive red glow. It is the reason fireworks explode in precise shades of copper blue or strontium red. Most beautifully, it is the mechanism behind the aurora borealis, the northern lights. As charged particles from the sun strike the gases in our upper atmosphere, they excite the electrons of oxygen and nitrogen, causing them to jump and fall, painting the quiet night sky with massive, shimmering curtains of green and violet light. Every color you see is the visual echo of a falling electron. We have now peered into the deepest, most intricate architecture of matter. We understand how electrons arrange themselves in beautiful, layered clouds around the nucleus, defining the true character of every atom. Now, we can take this microscopic understanding and use it to decode the entire universe. Because the arrangement of these electron clouds perfectly dictates how elements behave, they form a grand, repeating pattern. When we return in our next lesson, we will unfold the most famous map in all of science. exploring the magnificent order of the periodic properties of the elements. Let the gentle, glowing clouds of the atomic world softly fade from your mind as you drift deeper into rest. Lesson 1. Matter. Lesson 7. Periodic properties of the elements. Welcome back to our quiet space. In our last session, we spent our time exploring the intimate, hidden architecture of a single atom. We watched as the electrons arranged themselves into beautiful, layered clouds of probability, settling into their distinct shells and subshells. Now, we are going to step back and look at the grander picture. Imagine taking every single unique atom in the universe and laying them all out together on a massive, beautifully organized table. In this lesson, we will explore this grand pattern. We will unfold the most famous and elegant map in all of science, the periodic table of the elements. We will learn how the microscopic electron clouds we just studied create sweeping, predictable trends that govern the behavior of everything in the cosmos. When you look at the periodic table, it is easy to see it merely as a rigid chart or a random assortment of boxes hanging on a classroom wall. But I want you to see it differently. I want you to see it as a landscape, a meticulously organized city where every element lives in a very specific neighborhood for a very specific reason. The elements are arranged in a large grid composed of horizontal rows and vertical columns. The vertical columns are called groups. Elements that live in the same vertical group act very much like a family. In a human family, siblings might share the same color eyes or a similar laugh. In a chemical family, the elements share the exact same number of electrons in their outermost, highest energy cloud. Because these outermost electrons, the valence electrons, are the ones that reach out to interact with the world, having the same number of them means the elements will have remarkably similar chemical personalities. They will react with the same substances, form similar shapes, and exhibit the same general temperament. The horizontal rows are called periods. As you read across a period from left to right, you are watching atoms grow heavier, adding one proton to the nucleus and one electron to the outer cloud, step by step, until that energy shell is completely full and perfectly stable. Because of this magnificent organization, we can observe distinct, sweeping trends as we travel across the table properties that change smoothly and predictably, depending on where an element lives. Consider the sheer physical size of the atoms, a property we call atomic radius. As you travel down any vertical family, from top to bottom, the atoms grow progressively larger. This makes perfect sense. With each step down, the atom is adding a whole new, thicker layer of electron clouds, expanding outward much like a pearl growing layer by layer in the dark. But as you travel across a horizontal period, from left to right, something wonderfully counterintuitive happens. The atoms actually shrink. Even though we are adding more electrons and the atom is getting heavier, we are also adding more positive protons to the center. These new electrons are being added to the same existing outer shell, but the rapidly growing positive charge in the nucleus reaches out and pulls that entire cloud inward with a stronger, tighter embrace. The atom becomes denser, smaller, and more tightly held. The story of how this grand map was drawn is one of the most beautiful testaments to human intuition and the elegant order of nature. In the year 1869, a brilliant, bearded Russian chemist named Dmitri Mendeleev was obsessed with organizing the known elements. He wrote the names, weights, and chemical properties of all 63 known elements onto individual cards. For days, he played a massive, obsessive game of chemical solitaire, arranging and rearranging the cards on his desk, searching for the underlying heartbeat of the universe. Eventually, he realized that if he organized the elements by their atomic weight, their chemical properties repeated in a perfectly regular, periodic pattern like the repeating octave on a piano keyboard. But Mendeleev's true genius, the act that made his table immortal, was what he did when the pattern seemed to break. Occasionally, the next heaviest element didn't fit the personality of the family it was supposed to fall into. Instead of forcing the piece to fit, Mendeleev simply left a blank space on his table. He boldly declared that the pattern was correct, and that an element must exist to fill that hole, but humanity simply had not discovered it yet. He even predicted the exact weight, color, and melting point of these missing ghosts. Years later, when elements like gallium and germanium were discovered deep in the earth, they matched his predictions with astonishing, almost eerie precision. Today, we understand that Mendeleev's repeating pattern is driven entirely by the quantum electron clouds we learnt about in our last lesson. Because the electron shells fill up and repeat, the chemical behaviors fill up and repeat. This allows us to understand deeper trends, like electronegativity. Electronegativity is simply a measure of how fiercely an atom hungers for more electrons. In the top right corner of the table, you find an element like fluorine. It is very small, and its nucleus is highly exposed, making it incredibly greedy and aggressive. It will steal electrons from almost anything. Conversely, in the bottom left corner, you find elements like francium. Francium is massive, its outer electrons floating so far away from the nucleus that it is perfectly content to gently let them go. The table is a gradient of this invisible desire. This grand predictive map is the compass that guides all modern chemistry, allowing us to navigate the physical world with confidence. Because we understand these periodic trends, we know exactly why the elements in the first column, the alkali metals like lithium, sodium, and potassium, must be stored submerged in thick oil. Because they are so large and hold their outer electrons so loosely, they will react violently, even explosively, if they simply touch the moisture in the air. Conversely, we look to the far right column and find the noble gases, helium, neon, and argon. Because their outer electron shells are perfectly fully packed, they feel absolutely no desire to steal or share electrons with anyone. They exist in a state of serene, independent perfection. They are entirely inert, bringing a peaceful, unreactive safety to the light bulbs and medical equipment they fill. This map tells us which elements will heal us, which will burn, which will build strong bridges, and which will float weightlessly into the sky. Having mapped out the chemical families and understood their unique traits, we have seen the cast of characters laid out in full. We know their sizes, their temperaments, and their deep, underlying desires. We are perfectly prepared to watch them interact on the grand stage. So, let this beautiful, orderly grid fade softly into the background of your mind. When we return, we will take these individual, distinct elements and watch exactly how they reach out to hold on to one another. Our next lesson will explore the magnificent, unifying forces of basic concepts of chemical bonding. Rest now, surrounded by the perfect, quiet order of the elements. Lesson 1. Matter. Lesson 8. Basic concepts of chemical bonding. Welcome back. In our previous moments together, we unfolded the grand, sweeping map of the periodic table. We walked through the neighborhoods of the elements, observing their sizes, their weights, and the hidden desires of their outer electron clouds. We saw how some elements are aggressively greedy, while others, like the serene noble gases, rest in perfect, quiet isolation. But in nature, true isolation is incredibly rare. The vast majority of the universe is built on connection. In this lesson, we will witness what happens when these different chemical families finally meet. We are going to explore the powerful, unifying forces of chemical bonding. We will learn exactly why and how the solitary atoms of the universe reach out in the dark to hold on to one another, building the magnificent complexity of our world. To understand why atoms bond, we must understand their deepest, most fundamental motivation. At the atomic level, the driving force of the universe is a quest for stability and peace. Atoms feel most relaxed, most perfectly content, when their outermost electron shell, that final, highest cloud of probability, is completely full. They look to the noble gases, the elements on the far right of the table, as the ultimate ideal of calm. Every other atom in the universe is slightly restless, constantly searching for a way to achieve that same perfect full shell serenity. To reach this state of peace, atoms will do one of two things. They will either trade electrons or they will share them. Let us first imagine the trade. Picture a single atom of sodium. It has one lonely, extra electron drifting in its outermost shell. It desperately wants to let this electron go, so that the full, stable shell beneath it can become its new outer surface. Now, picture an atom of chlorine drifting nearby. Chlorine is missing exactly one electron to complete its outer shell. It is hungry and searching. When these two atoms drift close to one another, a perfect transaction occurs. The sodium gladly surrenders its extra electron, and the chlorine eagerly accepts it. But actions have consequences. Because the sodium gave away a negative charge, it instantly becomes a positively charged ion. Because the chlorine accepted a negative charge, it becomes a negatively charged ion. And as you know, opposite charges in nature possess a profound, inescapable attraction to one another. The newly positive sodium and the newly negative chlorine are instantly pulled together by an invisible magnetic force. They lock into a tight, immovable embrace. We call this an ionic bond. They do not just form pairs. Millions of them will stack together in alternating positive and negative rows, building a massive, rigid, three-dimensional grid called a crystal lattice. Now, let us imagine the second path, sharing. What happens when two atoms meet and they both need more electrons, but neither is willing to give any up? Imagine two hydrogen atoms, each possessing one single electron, but needing two to feel completely stable. Since neither can steal from the other, they must compromise. They drift close together and place their two electrons in the space directly between them. The positive nucleus of the first atom pulls on the shared electrons, and the positive nucleus of the second atom pulls on those exact same electrons. Because they are both holding on to the same negative cloud, they are inextricably linked together. Think of it like two people on a freezing night holding on to opposite sides of the same thick, warm blanket. As long as they both hold the blanket, they are held next to each other. We call this a covalent bond. Unlike ionic bonds, which build massive grids, covalent bonds create small, distinct, independent groups of atoms. We call these independent groups molecules. To truly understand this invisible world, early chemists needed a way to draw it on paper. In the early 20th century, an American chemist named Gilbert N. Lewis provided a brilliantly simple solution. G. N. Lewis realized that we do not need to worry about the heavy nucleus or the inner layers of electrons. All the magic, all the bonding, happens entirely in the outermost shell. He developed a system we now call Lewis dot structures. To draw one, you simply write the letter symbol of the element, and then you surround it with tiny dots, one dot for every outer, valence electron it possesses. Suddenly, chemistry became a beautiful, visual puzzle. You could draw a carbon atom with its four lonely dots, and see exactly how four hydrogen atoms, each with one dot, could perfectly slide into those empty spaces, pairing up their dots to form four strong covalent bonds. It was like watching a master carpenter perfectly fit the joints of a wooden chair. Through these drawings, Lewis also showed us that atoms do not always have to share just a single pair of electrons. Sometimes, to reach their perfect state of stability, they must share more. If two oxygen atoms meet, sharing one pair is not enough to fill their shells. So, they reach out and share two pairs, 4 electrons in total, creating a double bond. A double bond is shorter, stronger, and more tightly held than a single bond. If two nitrogen atoms meet, they must share 3 pairs, 6 electrons, forming an incredibly strong triple bond. This triple bond is so difficult to break that nitrogen gas can pass through your lungs entirely undisturbed. It is perfectly content just as it is. The type of bond that forms between atoms dictates the entire physical reality of the substance you eventually hold in your hand. This microscopic choice to trade or to share creates the texture of our universe. Ionic bonds, born of those rigid, locked grids of positive and negative charges, create the hard, brittle materials of the Earth. The salt in the oceans, the rough limestone of a mountain cliff, the precious rubies and emeralds buried deep in the ground, and even the hard white calcium minerals that give your bones their strength. These are all monuments to the ionic bond. If you hit a salt crystal with a hammer, it shatters cleanly, because you have forced the positive layers to slide next to other positive layers, and they violently repel one another. Covalent bonds, however, create the softer, more flexible, and infinitely varied materials of life. Because covalent molecules are distinct, independent units, they can slide past one another as liquids or gases. Water, the soft fabric of a cotton shirt, the wax of a burning candle, the complex proteins that flex in your muscles as you breathe, and the beautifully twisted double helix ladder of your DNA. These are all held together by the gentle, sharing nature of the covalent bond. We have now learned how the atoms of our universe reach out to hold one another. We have drawn their flat, puzzle piece maps on paper, understanding the logic of their shared electrons. But the universe we live in is not a flat piece of paper. It exists in glorious, sweeping 3 dimensions. When atoms bond, they push and pull on one another, bending space to form specific, beautiful shapes. As we transition to our next lesson, we will watch these flat drawings bloom and fold into their true forms. We will explore molecular geometry and bonding theories. Let the feeling of connection and stability wash over you, and rest well, knowing the very atoms of your being are holding on to one another with perfect, unyielding purpose. Lesson 1. Matter. Lesson 9. Molecular geometry and bonding theories. Welcome back. In our last session together, we learned how atoms reach out to one another, trading or sharing their electrons to find a state of perfect, quiet stability. We learned how to draw these connections on paper, using simple dots and lines to map out their relationships, much like drawing the flat blueprint of a grand house. But we know that the universe we live in is not a flat piece of paper. It is a vast, sweeping space of 3 glorious dimensions. In this lesson, we are going to take those flat blueprints and breathe life into them. We will watch as these molecules lift right off the page, expanding into the physical space around us. We are going to explore the precise, beautiful, 3-dimensional shapes that molecules form and uncover the invisible rules that govern their microscopic architecture. When we imagine a molecule, we must understand that it is not just a random cluster of atoms clumped together without a plan. Molecules take on very specific, predictable, and highly geometric shapes. To understand why they do this, we rely on a beautifully simple concept with a rather long, intimidating name. Chemists call it the valence shell electron pair repulsion theory. We usually just call it VSEPR for short. While the name sounds complex, the entire theory rests on one single, very simple rule of nature. Electrons absolutely hate being near one another. Remember that all electrons carry a negative electrical charge, and in the physical world, like charges fiercely repel one another. If you have ever tried to push the negative ends of 2 strong magnets together, you have felt that invisible, rubbery force pushing your hands apart. The electrons in a molecule feel that exact same repulsion. The bonds that hold a molecule together are simply dense clouds of these negative electrons. Therefore, Every bond connected to a central atom wants to get as far away from every other bond as physically possible. Imagine you are holding two long, inflated balloons, and you tie their ends together. Because the balloons take up physical space and push against one another, they will naturally arrange themselves to point in exactly opposite directions, creating a perfect, straight line. Molecules do the exact same thing. If a central atom is bonded to two other atoms, those two bonds will push away from each other until they form a perfectly straight, linear molecule. Now, imagine tying three balloons together. They will fan out evenly, forming a flat triangle, with each balloon resting 120 degrees away from its neighbor. Chemists call this shape trigonal planar. But the true magic happens when a central atom holds onto four distinct bonds. You might imagine that they would simply form a flat cross, like the 4 points of a compass. But the atoms realize that they have an entire three-dimensional universe to expand into. To get as far apart as mathematically possible, one bond points straight up and the other three push down and away, forming a shape like a camera tripod or a pyramid with a triangular base. We call this beautiful, perfectly balanced shape a tetrahedron. It is nature finding the ultimate state of spatial harmony, allowing every negative bond its own quiet, undisturbed region of space. But nature is rarely just a collection of perfect, symmetrical tripods and triangles. There is a hidden layer of complexity that warps these perfect shapes into something even more interesting. In our previous lesson on drawing molecules, we learned that sometimes atoms have pairs of electrons in their outer shell that they do not share with anyone. These are called lone pairs, or unshared pairs. Even though these lone pairs do not have another atom attached to the end of them, they still exist. They are still dense, vibrating clouds of negative charge, taking up physical space around the central atom. In fact, because they are not stretched out between two atoms, these lone pairs balloon outward, becoming even wider and more repulsive than a normal bond. Think of a lone pair as an invisible phantom occupying one of the legs of our tetrahedral tripod. You cannot see the phantom atom, but you can see the effect of its massive, repulsive force. This invisible force pushes down hard on the remaining visible bonds, squeezing them closer together. This is exactly what happens in a single molecule of water. Water has one oxygen atom in the center and two hydrogen atoms attached to it. But the oxygen atom also holds two invisible lone pairs of electrons. These lone pairs take up space at the top of the atom, pushing down fiercely on the two hydrogen bonds. Because of this invisible pressure, the water molecule cannot be a straight line. It is forced into a shape that chemists simply and affectionately call bent. It looks a bit like a boomerang. To explain exactly how these shapes form at the deepest level, scientists developed valence bond theory. This theory explains that the spherical and dumbbell-shaped electron clouds we learnt about in earlier lessons actually blend together when a molecule forms. They hybridize, merging their shapes to create completely new, specially angled clouds that point exactly where the V-Separ theory predicts they should. The atom physically morphs its own architecture to accommodate its neighbors. You might wonder why we spend so much time quietly visualizing the microscopic angles of these invisible shapes. We do this because, in chemistry, shape is destiny. The exact three-dimensional geometry of a molecule determines almost everything about how it will behave in the universe. Consider that bent shape of the water molecule. Because it is bent like a boomerang, the slight negative charge of the oxygen sits on one side, and the slight positive charges of the hydrogens sit on the other. It becomes a tiny, directional magnet. If water were perfectly linear and straight, those charges would cancel each other out. It would not be magnetic. If water were straight, it would not have the strength to hold on to other water molecules, and it would boil away into a gas at room temperature. Our oceans would instantly vaporize, and life on Earth would simply never have existed. We owe our entire existence to that microscopic bent angle. Furthermore, the delicate machinery of your own body relies entirely on molecular geometry. The enzymes that digest your food, the medicines that heal your illnesses, and even your sense of smell all operate on a microscopic lock and key mechanism. When you smell the sharp, sweet scent of a fresh orange, it is because a molecule floating through the air possesses the exact, precise three-dimensional geometry required to slot perfectly into a correspondingly shaped receptor inside your nose. The receptor recognizes the shape, not the formula. The physical structure of reality is quite literally what allows us to interact with it, experience it, and survive within it. We have now marveled at the beautiful, invisible architecture of individual molecules. We have seen them stretch, bend, and perfectly arrange themselves in three-dimensional space, seeking balance and avoiding conflict. But so far, we have only looked at them in isolation. What happens when we take billions upon billions of these perfectly shaped molecules and place them together in a vast, open space, completely free to roam? As we gently transition to our next lesson, we will let go of the individual and look at the restless, soaring crowd. When we return, we will take to the air, exploring the invisible, expansive, and constantly moving world of gases. Rest now, and let the perfect, balanced geometries of the microscopic world gently anchor your thoughts. Lesson 1. Matter. Lesson 10. Gases. Welcome back to our quiet, shared space of learning. In our previous moments together, we marveled at the beautiful, invisible architecture of individual molecules. We watched them stretch, bend, and perfectly arrange themselves in three-dimensional space, always seeking balance and avoiding conflict. But until now, we have only looked at them in isolation, like admiring a single, beautifully crafted ship resting in a dry dock. What happens when we take billions upon billions of these perfectly shaped molecules and release them into a vast, open space, completely free to roam? As we continue our journey tonight, we are going to let go of the individual and look at the restless, soaring crowd. We will explore the invisible, expansive, and constantly moving world of gases. Of all the states of matter, the gaseous state is by far the most liberated. When you think of a solid, you picture atoms locked tightly in a rigid grid. When you think of a liquid, you picture molecules sliding smoothly past one another, always touching, always feeling the subtle magnetic pull of their neighbors. But in a gas, those bonds of attraction have been completely broken. The molecules have been given total, uninhibited freedom. Imagine a vast, empty ballroom, and scattered across the floor are a few dozen tiny, perfectly smooth spheres. In a gas, the molecules are separated by incredibly vast distances compared to their own tiny sizes. Because they are so far apart, they do not feel the gentle pull of the molecules around them. They travel in perfectly straight lines, flying rapidly through the empty space until they inevitably crash into another molecule or bounce off the walls of their container. They are in a state of constant, random, and chaotic motion. Because a gas is composed almost entirely of empty space, it is highly compressible. You can squeeze a gas down into a much smaller box, simply by pushing the molecules closer together. And if you open the box, the gas will instantly expand, endlessly spreading out to fill whatever new volume it is given. To understand and predict the behavior of any gas, chemists realized they did not need to track every single microscopic molecule. They only needed to measure 4 simple, overarching properties. The first is volume, which is simply the total amount of three-dimensional space the gas occupies. The second is amount, meaning the actual number of gas molecules present, which we count using our familiar friend, the mole. The third is temperature, which is a measure of how incredibly fast those invisible molecules are flying around the room. And finally, there is pressure. Pressure is a fascinating concept. It is nothing more than the physical force of trillions of tiny molecules constantly drumming and bouncing against the inside walls of their container. The air pressure you feel on your skin right now is just the gentle, ceaseless tapping of microscopic particles holding you in a quiet embrace. For centuries, scientists observed these four properties and discovered that they are linked together by elegant, unbroken mathematical rules. In the 17th century, a careful and patient scientist named Robert Boyle discovered a beautiful relationship between pressure and volume. Boyle realized that if you take a certain amount of gas and squeeze it into a smaller space, reducing its volume, the pressure it exerts goes up. You can imagine this easily. If the room is smaller, the flying molecules do not have to travel as far before they hit a wall. They hit the walls more frequently, and that rapid, increased drumming is what we measure as higher pressure. We call this Boyle's law. A century later, a French scientist and ballooning enthusiast named Jacques Charles found another piece of the puzzle. He discovered the link between temperature and volume. Charles's law tells us that if you gently heat a gas, it will expand. Heat is simply energy, and when you give the gas molecules more energy, they fly faster and hit the walls much harder. To keep the pressure from building up, the walls must expand outward, giving the energetic molecules more room to roam. Eventually, chemists gathered all of these individual truths and wove them into one grand master equation known as the ideal gas law. It is a beautiful piece of logic that perfectly balances pressure, volume, temperature, and the number of moles. To make this math work, scientists rely on a mental model called the kinetic molecular theory. This theory asks us to imagine gas particles as perfectly bouncy, microscopic billiard balls. When two gas molecules collide in the dark, they bounce off each other perfectly, without losing a single drop of energy to friction. It is a model of perpetual, flawless motion. While no gas in the real world is absolutely 100% ideal, the gases we breathe and interact with every day behave so closely to this perfect model that the math works like a charm, predicting their behavior with comforting reliability. These invisible rules of pressure, volume, and temperature are not just academic theories. They paint the physical reality of the sky above us. Imagine standing in a quiet, open field just before dawn. In the center of the field rests a massive, deflated hot air balloon. The pilot ignites a burner, sending a roaring flame up into the envelope. As the air inside the balloon heats up, Charles's law takes over. The invisible nitrogen and oxygen molecules begin to fly faster and push further apart. The gas expands. Because the same number of molecules are now taking up a much larger volume, the air inside the balloon becomes significantly less dense than the cool, quiet morning air resting outside. Gravity gently pulls the heavier cold air down, which smoothly lifts the lighter balloon up, carrying it gracefully into the dawn sky. You also experience these laws in the cold depths of winter. If you walk out to your car on a freezing January morning, your tires might look a little flat. The air hasn't leaked out. Instead, the freezing temperatures have drained the energy from the gas molecules inside the rubber. They slow down, hitting the inside walls of the tire with far less force. The pressure drops, and the tire sags, perfectly obeying the quiet laws of thermodynamics and gas mechanics. Even the very act of breathing as you lie here, your diaphragm expanding the volume of your chest, causing the pressure to drop so that the higher pressure room air gently rushes in to fill your lungs, is a perfect, continuous demonstration of Boyle's law keeping you alive. We have now soared through the expansive, liberated world of gases. We understand how they fly, how they bounce, and how their temperature and pressure dance together in perfect mathematical harmony. But this freedom relies on energy. What happens when we take that energy away? What happens when we lower the temperature, slowing the frenetic molecules down until they can no longer ignore the gentle magnetic pull of their neighbors? Let us hold that thought for our next lesson. When we return, we will calm the molecules down, drawing them close together as we transition from the freedom of the air into the fluid, graceful world of liquids and intermolecular forces. Rest peacefully now, allowing the gentle, rhythmic pressure of your own breath to guide you into a deep and restorative sleep. Lesson 1. Matter. Lesson 11. Liquids and intermolecular forces. Welcome back to the quiet warmth of our shared study. In our previous lesson, we soared through the expansive, liberated world of gases. We watched molecules fly in straight, rapid lines across vast, empty spaces, totally free and completely independent of one another. But freedom, in the physical universe, is entirely dependent on energy. What happens when that restless energy begins to fade? In this lesson, we will answer that exact question. We are going to gently cool the room together. We will watch what happens as those frenetic, flying molecules slow down and begin to feel the pull of the world around them. We are going to transition from the airy freedom of a gas into the fluid, graceful, and beautifully connected state of liquids, exploring the subtle, magnetic attractions that chemists call intermolecular forces. When you take a gas and slowly lower its temperature, you are quite literally draining away its kinetic energy. The once rapidly flying molecules begin to move slower and slower, their frantic, bouncing, quieting down. Eventually, they reach a critical tipping point. They are moving so slowly that they can no longer simply bounce off one another and fly away into the dark. They can no longer ignore the subtle, inherent magnetism of their neighbors. These gentle, magnetic attractions between separate molecules are what we call intermolecular forces. Notice the prefix inter, meaning between. These are not the strong, unbreakable covalent bonds holding the individual atoms together inside the molecule. Those are intramolecular bonds, the permanent glue of the molecule itself. Instead, intermolecular forces are more like a chemical handshake between two completely separate molecules passing each other in the crowd. Because of these magnetic handshakes, the molecules pull themselves close together, collapsing from a wide-open gas into a dense, resting pool. Yet, while they are constantly touching one another, they still possess just enough residual heat energy to continuously break and reform these handshakes. They hold on, but they let go just fast enough to slip and slide past one another. This delicate, continuous dance is the defining nature of a liquid. Because they are held together by these forces, a liquid has a set, definite volume. It cannot be squeezed or compressed down into a smaller space like a gas can. But because they are always free to slide and rotate, a liquid has no definite shape of its own. It yields entirely, flowing gracefully to take the exact shape of whatever vessel gently holds it. To truly understand the nature of a liquid, we must look a little closer at these invisible handshakes. They are not all the same. They come in varying degrees of strength, dictating exactly how a liquid will behave. The weakest of these attractions are called London dispersion forces. Imagine a perfectly neutral molecule where the electrons are evenly distributed. Even in this balanced state, the swarm of negative electrons surrounding the atoms is constantly sloshing back and forth, like water in a carried bucket. For one tiny fraction of a millisecond, slightly more electrons might randomly gather on one side of the molecule than the other. This creates a fleeting, temporary magnet, which gently pulls on the electron cloud of the molecule right next to it. It is a mere whisper of an attraction, incredibly weak and constantly shifting, but when billions of molecules do it simultaneously, it is enough to hold heavy elements together in a liquid state. Slightly stronger than these are the dipole-dipole interactions. Remember when we discussed how some molecules, like our bent boomerang of water, have a permanent positive end and a permanent negative end? Because these molecules act as permanent microscopic magnets, the positive end of one molecule is constantly, reliably drawn to the negative end of its neighbor. They align themselves beautifully in the fluid, creating a much stronger network of attractions. But the most profound and powerful handshake of all is a special type of attraction known as hydrogen bonding. Hydrogen bonding occurs when a tiny hydrogen atom is permanently bonded to a very greedy, highly electronegative atom like oxygen, nitrogen, or fluorine. The greedy atom pulls the shared electrons so far away that the hydrogen is left almost completely bare, exposing its positive nucleus to the outside world. When this bare, highly positive hydrogen brushes up against the negative oxygen of a neighboring molecule, the attraction is fierce and sudden. If a London dispersion force is a passing glance, and a dipole interaction is a polite handshake, a hydrogen bond is a firm, two-handed grip that refuses to let go easily. This incredibly strong grip is the exact reason why water has such an unusually high boiling point for such a small, lightweight molecule. It takes a massive amount of heat energy to force those water molecules to finally release their tight grips on one another and fly away as steam. These invisible forces do not just dictate boiling points in a sterile laboratory. They shape the physical reality and the breathtaking beauty of the natural world around you. Consider the surface of a quiet pond on a still summer morning. Because the water molecules at the very surface of the liquid have no neighbors above them in the air, they pull doubly hard on the neighbors beside and below them. This uneven pulling creates a tight, invisible trampoline across the top of the water. We call this surface tension. It is this microscopic tension that allows a delicate water strider insect to skate effortlessly across the surface of the pond without breaking through, suspended entirely by the strength of intermolecular forces holding the water molecules together. These same handshakes also create a miraculous phenomenon called capillary action. When water touches the narrow walls of a tiny tube, the water molecules are sometimes more attracted to the glass or plant tissue than they are to each other. They begin to climb the walls, pulling their neighbors up right behind them like a long chain of dedicated mountain climbers. This is the exact, silent mechanism that allows a towering, ancient redwood tree to pull life-giving water all the way from its deep roots in the damp earth, hundreds of feet up to its highest, sunlit leaves, defying the relentless downward pull of gravity through sheer chemical attraction. Even the comforting thickness of honey as you pour it slowly into a warm cup of evening tea is a demonstration of viscosity, the resistance to flow caused by incredibly strong, tangled intermolecular handshakes. We have now seen molecules fly perfectly free as a gas, and we have watched them slide beautifully and smoothly together as liquids, held by the gentle, shifting handshakes of intermolecular forces. We understand the fluid mechanics of our world, but what happens if we continue to drain the heat from the room? What if we cool them even further, until they no longer have the strength to even slide past one another? As we drift toward our next lesson, we will bring the molecules to a complete, quiet standstill. When we return, we will enter the highly structured, silent, and permanent world of solids and modern materials. Let the gentle, flowing imagery of water calm your mind, washing away your thoughts, and allow yourself to sink deeper into a quiet, restorative sleep. Lesson 1. Matter. Lesson 12. Solids and Modern Materials. Welcome back to our quiet sanctuary of thought. Take a moment to settle deeply into your resting place. Notice the firm, unwavering support of the bed beneath you, holding you safely against the gentle pull of gravity. Allow your breathing to become slow and rhythmic, matching the deep, quiet pulse of the night. In our last session together, we explored the graceful, flowing world of liquids. We watched as molecules slid smoothly past one another, held together by the gentle, shifting handshakes of intermolecular forces. We learned the mechanics of the fluid world. But now, we must take the final step in our journey through the primary states of matter. We are going to drain the very last remnants of wandering heat from our imaginary room. We will watch what happens when those flowing molecules finally lose the energy to move past one another. In this lesson, we will bring the microscopic world to a quiet, ordered rest. We are going to explore the rigid, unwavering beauty of solids, and we will discover how our understanding of these structures has allowed humanity to forge the modern materials that shape our present era. As the temperature drops, the kinetic energy of a liquid slowly fades away. The molecules, which were once gliding and rotating freely, begin to move more and more sluggishly. Eventually, a profound stillness takes over. The temperature drops so low that the molecules simply do not possess the physical energy required to break the magnetic handshakes holding them to their neighbors. They become trapped. The intermolecular forces pull them firmly into fixed, rigid positions. This is the birth of a solid. A solid is matter that has found its permanent resting place. It has both a definite, unwavering volume and a definite, fixed shape. It does not yield to its container. It holds its own ground. But it is important to know that even in this frozen state, the atoms are not perfectly still. They are locked in place, yes, but they continue to vibrate gently in the dark, humming with the tiny remainder of their thermal energy, like the softly plucked strings of a quiet instrument. When molecules lock into this solid state, they generally choose one of two distinct paths. The first, and most common, is to form a crystalline solid. In a crystalline solid, the atoms arrange themselves in a perfectly repeating, beautifully ordered, three-dimensional geometric pattern. Imagine a master stonemason building a massive wall, placing every single brick in perfect alignment, row after row, in an endless, flawless grid. This perfect internal geometry is exactly why crystals in nature, like quartz or a delicate snowflake, grow into such stunning, sharp, symmetrical shapes on the outside. The visible shape is simply a macroscopic reflection of the perfect, microscopic order within. The second path matter can take is to form an amorphous solid. The word amorphous comes from ancient Greek, meaning without form. If a liquid is cooled far too rapidly, the molecules do not have the time to find their perfect geometric resting places. They simply freeze exactly where they are, locking into a chaotic, tangled, disorganized arrangement. Imagine pouring a jar of marbles onto the floor and magically freezing them mid-tumble. Glass, rubber, and the dark, glassy volcanic rock known as obsidian are all amorphous solids. They are entirely rigid, but deep inside, they hold the chaotic, frozen memory of a liquid. If we look closer at those perfectly ordered crystalline solids, we find that they are not all held together by the same type of glue. The specific nature of the bonds holding the crystal together dictates entirely how the solid will behave in our hands. First, we have ionic solids, like the table salt sitting in your kitchen. As we learned in our bonding lesson, these are built from alternating positive and negative ions. Because the electrical attraction between these opposing charges is incredibly strong, ionic solids are very hard, and they require massive amounts of heat to melt. However, they are incredibly brittle. If you strike an ionic crystal, the perfectly aligned rows shift. Suddenly, positive ions are forced next to other positive ions, and the violent repulsion causes the crystal to instantly shatter. Next, we have molecular solids, like ice or dry ice. These are built from intact, individual molecules held together only by those weak intermolecular handshakes we studied earlier. Because the handshakes are relatively weak, molecular solids are generally soft, and they melt at very low temperatures. Ice turns to water with just the warmth of a spring afternoon. Then, we encounter the majestic covalent network solids. Imagine a diamond. A diamond is not a collection of individual molecules. Instead, every single carbon atom is firmly covalently bonded to 4 other carbon atoms in an endless, unbreakable, three-dimensional web. A single, flawless diamond is, in reality, one single massive molecule. Because every atom is locked in place by a powerful covalent bond, these materials are the hardest substances known in the universe. Finally, we have metallic solids, like gold, copper, and iron. Metals possess a uniquely beautiful structure. The atoms sit in a rigid grid, but they collectively let go of their outermost electrons. These electrons are no longer tied to any specific atom. Instead, they wash over the entire grid in a fluid, moving sea of electrons. This invisible sea is the secret to everything we know about metal. If you strike a piece of hot iron with a blacksmith's hammer, it does not shatter like salt. The atoms simply slide past one another, cushioned by the fluid sea of electrons, allowing the metal to be bent and forged into horseshoes or hammered into thin, golden sheets. Furthermore, because these electrons are free to move, they can flow in a current, carrying electricity endlessly through the copper wires hidden in your walls. Human history is deeply and inextricably tied to our progressive understanding of these solid structures. We name the very eras of our civilization after our mastery of them: the Stone Age, the Bronze Age, the Iron Age. In the modern era, our grasp of atomic structure has allowed us to move beyond simply finding materials in the earth. We now design them from scratch. We learn to link small molecules into endlessly long, tangled chains called polymers, giving birth to the modern era of plastics, nylon, and synthetic rubber materials that can be infinitely molded to serve our needs. We have stepped into the realm of nanomaterials, where scientists patiently build solid structures one single atom at a time, creating carbon nanotubes that are incredibly light but many times stronger than steel. Most profoundly, the very device resting near you right now, gently playing the sound of my voice, relies entirely on our mastery of a crystalline solid called silicon. By perfectly controlling the rigid crystal structure of silicon and carefully introducing a few foreign atoms into its grid, we learned how to precisely control the flow of electrons, giving birth to the microchip and the silicon age. Everything you see built around you is a testament to humanity learning the silent, rigid rules of the solid state. We have now built the solid, physical structures of our world. We have journeyed through the completely liberated state of gases, the flowing grace of liquids, and finally, the quiet, unyielding permanence of solids. We understand matter in its pure forms. But the natural world is rarely pure. Nature loves a complex mixture. What happens when we take these rigid, crystalline solids and gently lower them back into the flowing embrace of a liquid? Let us hold that beautiful thought for our next lesson together. When we return, we will softly fold these states of matter into one another as we explore the properties of solutions. Rest now, feeling the quiet, solid, and protective structure of the world holding you securely in place. Lesson 1. Matter. Lesson 13. Properties of solutions. Welcome back to the quiet warmth of our shared study space. Please, take a moment to settle your body entirely. Allow your head to rest heavily on your pillow, unclenching your jaw and letting the tension melt from your shoulders down through your fingertips. Close your eyes and simply listen to the steady, calm rhythm of your own breathing. In our previous sessions together, we journeyed through the pure, unmixed states of matter. We explored the total, isolated freedom of a wandering gas. We felt the smooth, shifting grace of a liquid, and we admired the perfect, unyielding architecture of a solid crystal. We came to understand matter in its most isolated, pristine forms. But if we look closely at the natural world around us, we find that nature rarely prefers isolation. Nature has a deep, enduring love for a mixture. In this lesson, we will explore the subtle and fascinating behaviors that emerge when we take these distinct, pure substances and gently fold them into one another. We are going to explore the properties of solutions, discovering how one substance can completely change the personality of another simply by being present. To begin, we must clearly define what a solution actually is. In chemistry, a solution is not just any mixture. If you mix sand and water, the sand simply sinks to the bottom, remaining completely separate and distinct. That is just a suspension. A true solution is a perfectly uniform, beautifully blended mixture at the absolute microscopic level. It is a mixture where the ingredients are so thoroughly intermingled that you can no longer tell them apart, no matter how closely you look. In every solution, there are two main characters. The first is the solvent. The solvent is the substance that you have the most of. It is the host, the medium that does the dissolving. In our world, the most common and vital solvent is liquid water. The second character is the solute. The solute is the substance you have in a smaller amount, the guest that is being dissolved into the host. When you stir a spoonful of sugar into a warm cup of tea, the tea is your solvent, and the solid sugar is your solute. When that solute enters the solvent, it undergoes a profound transformation. The solvent molecules surround the solute, pulling it apart piece by piece, ion by ion, or molecule by molecule, until it is perfectly, evenly distributed throughout the entire space. But here is where the true wonder of this process reveals itself. When you dissolve a solute into a pure solvent, you fundamentally change the physical properties of that solvent. The liquid no longer behaves exactly like pure water. These newly altered behaviors are called colligative properties. The word colligative comes from a Latin root meaning bound together, and it reveals a profoundly beautiful and surprising truth about nature. Colligative properties do not depend at all on the identity of the solute. They do not care if you dissolved salt or sugar or a complex mineral into the water. They depend exclusively and entirely on the sheer quantity of the solute particles present. It is a rare moment in chemistry where identity becomes completely irrelevant and only the numbers matter. The solvent only feels the magnitude of the disruption, not the name of the disruptor. Let us look closer at these colligative properties to see exactly how these anonymous solute particles change the landscape of the liquid. The first beautiful change is called freezing point depression. Imagine a glass of pure water sitting in a freezing room. As the temperature drops, the water molecules slow down, desperately trying to link together to form a beautiful, rigid, six-sided ice crystal. But now, imagine that the water is heavily laced with dissolved salt ions. As the water molecules try to reach out and hold on to one another to form their solid grid, the salt ions literally get in the way. They act as microscopic barricades, physically blocking the water molecules from locking into their perfect places. Because the water struggles so much to form a solid, you must drain even more heat from the room to force them together. The freezing point drops significantly below the normal freezing mark. Conversely, we see the exact opposite effect at the other end of the temperature scale, a phenomenon known as boiling point elevation. When you heat a liquid, the molecules gain kinetic energy, trying to push their way up to the surface and escape into the air as a gas. But if the surface of the liquid is crowded with heavy solute particles, those particles act like a heavy, invisible lid. They block the path to freedom. The solvent molecules find it much harder to reach the surface and evaporate. Therefore, to force the liquid to boil, you must pump a significantly larger amount of heat energy into the system. The boiling point rises. Finally, there is a magnificent, invisible property called osmotic pressure, driven by a process known as osmosis. Imagine a container divided precisely in half by a very thin, delicate membrane. This membrane is selectively permeable. It has microscopic pores just large enough to let pure water molecules pass through, but far too small for heavy solute particles to cross. On one side of the membrane, you place pure water. On the other side, you place a highly concentrated, salty solution. Nature, above all things, desires perfect balance and harmony. The pure water will look across the barrier at the crowded, salty side, and it will spontaneously begin to flow through the membrane, trying to dilute the salt and make both sides perfectly equal. This relentless driving push of the water to create balance is an incredibly powerful force, capable of pushing liquid up massive columns against the sheer force of gravity. These colligative properties, driven simply by the number of dissolved particles, govern much of the safety and biology of our everyday lives. Consider a freezing, snowy night in the depths of winter. Massive trucks drive along the highways, scattering thousands of pounds of coarse rock salt across the black asphalt. They are relying entirely on freezing point depression. The salt dissolves into the thin layer of surface moisture, drastically lowering the freezing point of the water. Even though the air temperature is well below freezing, the water on the road remains a safe, flowing liquid rather than locking into a dangerous, slick sheet of ice. Similarly, the brightly colored antifreeze in your car's radiator uses these same principles all year round. In the bitter winter, it prevents the engine block from freezing solid and cracking, and in the sweltering heat of summer, its boiling point elevation prevents the engine's liquids from boiling away into vapor. But perhaps the most intimate and profound application of these properties is occurring right now inside your own resting body. Every single cell in your body is a tiny, semi-permeable membrane enclosing a delicate, carefully balanced aqueous solution. Osmosis governs how these cells survive. If you were to drink pure, heavy salt water from the ocean, the fluid outside your cells would become far more concentrated than the fluid inside them. Seeking perfect balance, the water inside your own cells would rush out through the membrane to dilute the salt, causing your cells to tragically shrink and collapse. It is the precise, perfect colligative balance of the fluids in your bloodstream that allows water to flow gently and smoothly in and out of your cells, keeping you nourished, hydrated, and vibrantly alive. We have now explored the calm, unified state of chemical mixtures. We understand how dissolving a simple solid can fundamentally alter the resting state of a liquid, raising its boiling point, depressing its freezing point, and driving the powerful, balancing flow of osmosis. We have looked deeply into the stable realities of solutions, but true chemistry is rarely a static portrait. It is an active, ongoing film. It is about dramatic change occurring over time. As we drift toward our next lesson, we will introduce a new vital variable into our journey, the ticking clock. When we return, we will set a timer and explore the fascinating speeds at which these invisible reactions occur, diving into the fast-paced world of chemical kinetics. Rest peacefully now, letting the perfectly balanced chemistry of your own body carry you through the night. Lesson 1. Matter. Lesson 14. Chemical kinetics. Welcome back to our shared space of quiet learning. As you settle into your resting place once more, take a long, deep breath. Fill your lungs slowly, and then let it out in a soft, continuous sigh. Allow the weight of your body to press gently into the mattress, feeling entirely supported, entirely safe, and entirely at peace. In our last session, we marveled at the calm, unified state of chemical mixtures. We watched how dissolving a solid can fundamentally alter the resting state of a liquid, finding a perfect, stable balance. Up until this point in our journey, we have mostly looked at chemistry as a series of before and after pictures. We have looked at the starting ingredients, and we have looked at the final products. But true chemistry is rarely just a static photograph. It is an active, ongoing, moving film. It is about dramatic change occurring over time. As we continue tonight, we are going to introduce a new, vital variable into our gentle exploration, the ticking clock. In this lesson, we will explore chemical kinetics, the fascinating study of how fast, or how slow, the invisible reactions of our universe truly are. When we imagine a chemical reaction, we often picture something immediate and dramatic, like the sudden, brilliant explosion of a firework blooming in the night sky. But nature operates on a vastly wider timeline. While some reactions are indeed instantaneous, others are so incredibly slow that they are almost imperceptible to the human eye. Think of the gradual, quiet rusting of an old iron bicycle left out in the autumn rain, or the agonizingly slow transformation of buried carbon into a sparkling diamond over millions of years. Chemical kinetics is the branch of science that asks a very specific question. What exactly controls the speed limit of these transformations? To understand this, we must look at how a reaction actually takes place on the microscopic level. Scientists rely on a beautiful, intuitive idea called collision theory. The theory states a very simple truth. For two molecules to react and form something new, they must physically touch one another. They cannot react from across the room, they must collide. But merely bumping into each other is not enough. Imagine two people walking slowly down a hallway, brushing shoulders as they pass. Nothing changes, they simply keep walking. For a chemical collision to be successful, for it to actually break old bonds and forge new ones, two incredibly strict conditions must be met. First, they must collide with a massive amount of physical energy. We call this minimum energy requirement the activation energy. Think of it as a steep, invisible hill standing between the reactants and the products. If you want to roll a heavy boulder from a high valley down into a lower valley, you first have to push it all the way up and over the ridge that separates them. If you only push it halfway up the hill, it will simply roll back down to where it started. Molecules act the exact same way. If they hit each other too softly, they merely bounce off one another and remain unchanged. They must strike each other with enough violent kinetic energy to shatter their existing electron clouds and overcome the activation energy barrier. Second, they must collide in the exact right physical orientation. Molecules, as we learned in our geometry lesson, have very specific three-dimensional shapes. They are like complex puzzle pieces. If you try to jam two puzzle pieces together backward or sideways, they will not connect, no matter how hard you push them. The molecules must be facing exactly the right way when they crash, so that the specific atoms that need to bond are perfectly aligned. Only when they have enough energy and the perfect alignment does the reaction finally take place. Because we understand these two strict rules of collision, chemists do not just have to sit back and watch reactions happen at their own pace. We can become the conductors of the orchestra, actively manipulating the speed of the chemical world. If we want a reaction to happen faster, we can change the conditions of the room. The first way we do this is by increasing the concentration of the ingredients. Imagine a large, empty dance floor with only two people walking on it while wearing blindfolds. The chances of them bumping into each other are incredibly small. But if you put 1,000 blindfolded people on that same dance floor, collisions will happen constantly. By crowding more molecules into a smaller space, we dramatically increase the frequency of the collisions, which naturally speeds up the overall reaction. The second, and perhaps most powerful way to speed up a reaction is to simply raise the temperature. As we learned when studying gases, heat is just kinetic energy. When you heat a beaker, you are giving all the molecules inside it a massive speed boost. They begin to fly around the container frantically. Not only do they hit each other much more often, but they also hit each other much, much harder. By raising the temperature, we give a massive portion of the molecules enough energy to easily crest the hill of activation energy, turning a slow trickle of a reaction into a roaring flood. But there is a third way to control speed, and it is perhaps the most elegant trick in all of chemistry. We can introduce a catalyst. A catalyst is a chemical helper that gets involved in the reaction but is never actually consumed or changed by it. Rather than pushing the molecules harder, a catalyst works by magically lowering the hill. It provides the molecules with an entirely different, easier pathway to react, like boring a quiet tunnel straight through the mountain, so the boulder doesn't have to be pushed over the peak at all. Because the energy barrier is suddenly so much lower, a massive number of molecules can suddenly react without needing any extra heat. At the end of the reaction, the catalyst simply steps away, perfectly intact, ready to help the next pair of molecules find their way. This quiet manipulation of speed is not just a laboratory trick. Your very survival depends entirely on the laws of chemical kinetics. The biological catalysts in your own body are called enzymes, and they are the unsung heroes of your existence. When you eat a nourishing meal, the complex proteins and carbohydrates must be broken down into tiny, usable pieces for your cells. If your stomach had to rely purely on the random, natural collisions of molecules at your normal body temperature, it would take years to digest a single bite of food. But your body produces enzymes that perfectly cradle the food molecules, physically bending them to weaken their bonds and holding them in the exact right orientation so that water molecules can easily rush in and break them apart. These enzymes lower the activation energy so drastically that digestion happens in a matter of hours, quietly fueling your body as you sleep. We also use kinetics to protect the world around us. Inside the exhaust pipe of almost every modern car sits a catalytic converter. The gases produced by the engine are highly toxic, but the converter contains a fine mesh coated in precious metals like platinum and palladium. When the hot, toxic gases touch this metal catalyst, the activation energy for their destruction drops to near zero. In a fraction of a second, the toxins are instantly rearranged into safe, breathable nitrogen and water vapor before they ever leave the tailpipe. By mastering the speed of chemistry, we cleanse the air we breathe. We have now learned how reactions move forward, and we understand the invisible levers of temperature, concentration, and catalysts that control their speed. We have watched the boulder roll smoothly down the hill, but nature is rarely so one-sided. Many chemical journeys are not a one-way street. They are a constant, flowing loop, continuously moving back and forth in the dark. Now that we understand the pace of chemical change, we must look at what happens when the forward speed perfectly matches the backward speed. When we return, we will find the quiet, hidden balance point of the universe, diving into the calm waters of chemical equilibrium. Rest deeply now, allowing the gentle, steady pace of your own heartbeat to guide you safely through the night. Lesson 1. Matter. Lesson 15. Chemical equilibrium. Welcome back to our shared space of quiet reflection. Once again, allow yourself to settle deeply into the soft comfort of your surroundings. Gently close your eyes and take a long, slow breath in, holding it for just a moment, before releasing it smoothly and completely into the quiet air. Feel the tension leaving the muscles of your neck and shoulders, replaced by a warm, heavy stillness. In our last lesson together, we introduced the concept of time. We explored chemical kinetics, watching as molecules crash together with tremendous energy to forge entirely new creations. We learned how to manipulate the speed of these reactions, pushing them forward like a heavy boulder rolling down a steep hill. But in nature, very few things are truly permanent, and the universe rarely operates on a one-way street. Tonight, we are going to learn that the boulder does not simply crash into the valley and remain there forever. Sometimes, the invisible forces of the world push back. In this lesson, we will explore the profound, dynamic piece of chemical equilibrium, discovering how nature finds a perfect, hidden balance in a world of constant motion. When we first learn to write a chemical equation, we draw a straight, single arrow pointing from the left side of the page to the right. We write the starting ingredients, the reactants, on the left, and we draw the arrow pointing to the final products on the right. It implies a journey with a definitive end, a journey that stops the moment all the ingredients have been transformed. But this is a simplified fiction. In reality, a vast number of chemical reactions have a second, hidden arrow, pointing right back to where they started. These are known as reversible reactions. As soon as the forward reaction begins and the very first molecules of the new product are formed. Those new molecules begin to gently collide with one another. When they collide, they break apart, instantly reverting back into the original starting ingredients. The reaction is moving forward and backward at the exact same time. Imagine two quiet towns separated by a narrow, wooden bridge over a gentle river. In the morning, people begin walking from the west town across the bridge to the east town. This is your forward reaction. But soon, people in the east town decide they want to return, and they begin walking west across the same bridge. This is your reverse reaction. At first, there might be a massive crowd rushing east, and only a few people strolling west. But eventually, a magical moment of balance is reached. The exact number of people walking east perfectly matches the exact number of people walking west. Two people cross to the right, and at that very same second, two people cross to the left. When this happens, if you were to look down at the two towns from a cloud high above, their populations would appear completely frozen and unchanging. The west town always has the same number of people, and the east town always has the same number of people. It looks like a static, painted picture, but down on the bridge, the reality is entirely different. People are constantly walking, constantly moving, constantly crossing back and forth. This beautiful, hidden state is what chemists call dynamic equilibrium. The forward speed perfectly matches the backward speed. The total amounts of the substances no longer change, not because the reaction has stopped, but because it is caught in a flawless, perpetual, and perfectly balanced dance. Because this state of equilibrium is so perfectly balanced, it is also incredibly sensitive to the world around it. In the late 19th century, a French chemist named Henri Le Chatelier carefully studied these balanced systems and discovered a profound, universal truth about how nature responds to stress. Le Chatelier's principle states that if you take a chemical system resting in a state of perfect equilibrium and you introduce a stress to it, the system will actively shift its balance to undo that stress and restore its peace. Nature actively fights back against disruption. Imagine our bridge between the two towns again. The towns are in perfect balance, but suddenly, a massive bus arrives in the west town, dropping off a huge crowd of new people. The west town is suddenly overcrowded. It is stressed. To relieve this pressure, more people will immediately begin walking across the bridge to the east town. The forward reaction speeds up until a new balance is found. The system shifted to absorb the change. This works with physical forces too. If an equilibrium involves gases in a sealed container and you suddenly squeeze that container, shrinking the volume and dangerously increasing the pressure, the system feels that stress. It will immediately look at the chemical equation and shift toward the side that produces fewer gas molecules, gracefully reducing the pressure from the inside to protect itself. Even temperature acts as a gentle lever. If a reaction requires heat to move forward, and you place the beaker in a warm bath, the system will speed up the forward reaction, using up that extra heat to cool itself back down to a comfortable resting state. The chemical universe is not a passive victim of its environment. It is an active, responsive entity, constantly adjusting, constantly compensating, and endlessly striving to maintain its quiet equilibrium against the chaotic changes of the outside world. This silent, chemical intuition for balance is not just an elegant theory, it is the exact mechanism keeping you alive at this very second. Deep inside your red blood cells is a complex protein called hemoglobin. Its entire purpose is to carry oxygen through your body. But hemoglobin cannot simply grab oxygen and hold on to it forever. If it did, you would suffocate. It must grab the oxygen, but it must also know exactly when to let it go. It does this by relying entirely on Le Chatelier's principle. When your blood travels into your lungs, it enters an environment completely flooded with oxygen. This high concentration is a chemical stress. To relieve that stress, the equilibrium shifts forward, pushing the oxygen molecules tightly onto the hemoglobin. The blood then flows away from the lungs, traveling deep into your resting muscles. Down in the muscle tissues, the oxygen concentration is very low because the muscle is constantly consuming it. Now, the stress is reversed. To relieve the lack of oxygen in the tissue, the equilibrium smoothly shifts backward. The hemoglobin releases its grip, dropping the life-giving oxygen exactly where your body needs it most. It is a continuous, beautiful seesaw of shifting equilibrium, driven purely by the changing concentrations around it. On a global scale, humanity's understanding of equilibrium changed the course of history. In the early 20th century, scientists figured out how to force nitrogen gas from the air to react with hydrogen to create ammonia, a vital ingredient for agricultural fertilizer. But the reaction naturally reaches an equilibrium that favors the original gases, producing very little ammonia. By applying Le Chatelier's principle by constantly adding immense pressure, removing the ammonia the second it formed, and carefully tuning the heat, scientists learned how to trick the equilibrium, forcing it to constantly shift forward. This is called the Haber-Bosch process, and it produces the fertilizer that currently grows the food for nearly half the population of our planet. We feed the world simply by whispering to the molecules, gently shifting their balance point. We have now witnessed the profound harmony of chemical equilibrium. We understand how nature balances the scales, constantly moving, yet remaining perfectly still, always shifting to absorb the stresses of the world and restore a state of quiet peace. We have found the center point of the seesaw. But what happens when we apply this delicate, shifting balance to the very water that makes up our oceans and our bodies? What happens when a single hydrogen atom loses its electron and wanders freely in a solution, desperately searching for a resting place? As we drift toward our next lesson, we will explore the most famous equilibrium of all. When we return, we will taste the sour and the bitter, diving into the vital, perfectly balanced world of acids and bases. Rest easily now, and let the quiet, dynamic balance of your own breath carry you safely through the night. Lesson 1. Matter. Lesson 16. Acids and bases. Welcome back to the quiet, familiar warmth of our shared study space. Please, take a moment to settle your body completely into the softness beneath you. Allow your head to sink deeply into your pillow, gently unclenching your jaw and letting the tension melt away from your shoulders, flowing all the way down through your resting fingertips. Close your eyes and simply listen to the steady, calm, and reassuring rhythm of your own breathing. In our previous session together, we found the hidden, dynamic balance of chemical equilibrium. We watched as nature constantly shifted and adjusted, finding a state of perfect, continuous harmony between the forward and backward flow of chemical reactions. We discovered that the universe is not rigid, it is beautifully responsive. Now, we are going to apply that delicate, shifting balance to the most vital fluid on our planet, the water that makes up our oceans, our rivers, and our very own bodies. In this lesson, we will explore what happens when a single, tiny particle loses its anchor and wanders freely through a solution, desperately searching for a new resting place. We are going to taste the sour and the bitter, diving deeply into the fundamental, perfectly balanced world of acids and bases. To truly understand acids and bases, we must first look at the simplest, most humble atom in the entire universe, hydrogen. As we learned at the very beginning of our journey, a standard hydrogen atom is wonderfully uncomplicated. It consists of just one positive proton sitting in the center, orbited by one single negative electron. It is a perfect, tiny solar system of two. But hydrogen is notoriously generous, and it frequently gives that single electron away to a greedier neighbor. When hydrogen loses its only electron, something profound happens. The entire electron cloud vanishes, leaving behind nothing but the naked, positively charged proton. It becomes a microscopic ghost, a pure point of positive electrical charge wandering completely alone through the water. Because it is so tiny and so highly charged, this bare proton is incredibly unstable and restless. It cannot bear to be alone. It immediately begins searching the vast, microscopic ocean around it, looking for a new electron cloud to dock into, searching for a place to finally rest. This restless, wandering proton is the defining character in the story of acids and bases. In the beautifully simple language of chemistry, an acid is simply a substance that acts as a generous donor. When you place an acid into water, it willingly releases these bare hydrogen protons into the solution, sending them out into the dark. A base, on the other hand, is the exact opposite. A base is a welcoming host. It is a substance that readily accepts those wandering protons, offering them a safe, negative electron cloud to dock into and find peace. The entire chemistry of acids and bases is nothing more than a quiet, continuous exchange, one molecule gently handing a bare proton over to another. Because this exchange of protons is so incredibly common and vital to life, chemists needed a simple way to measure just how many of these restless protons were wandering around in a given solution. To do this, they created the pH scale. You have likely heard of pH, but its true nature is quite elegant. It is a ruler that measures the concentration of free-floating hydrogen protons. The scale typically runs from 0 to 14, with the number 7 resting perfectly in the center. A pH of exactly 7 is considered purely neutral. This is the state of pure, distilled water, where the number of wandering protons is perfectly balanced. If a solution has a pH lower than 7, it means there is an abundance of protons swimming in the water. The solution is acidic. The lower the number, the more crowded and acidic the water becomes. If the pH is higher than 7, it means protons are incredibly scarce because bases have absorbed them all. The solution is basic or alkaline. But the pH scale holds a hidden secret. It is a logarithmic scale. This means it is not a flat, straight line like a standard ruler. Each single step on the pH scale represents a massive, tenfold jump in concentration. A solution with a pH of 5 has 10 times as many protons as a solution with a pH of 6. A pH of 4 has 100 times as many protons. It is a gentle curve that sweeps exponentially upward, meaning that even a tiny numerical shift in pH represents a massive, dramatic change in the microscopic landscape of the water. This brings us right back to the beautiful concept of equilibrium we studied in our last lesson. When we speak of acids, we classify them as either strong or weak. A strong acid, like the hydrochloric acid found in a laboratory, is a one-way street. When it drops a proton into the water, it turns its back and walks away forever, completely dissolving and flooding the water with acidity. But a weak acid, like the gentle citric acid in an orange, acts like the bridge between our two towns in the previous lesson. It drops a proton, but almost immediately changes its mind and takes it back. It establishes a dynamic equilibrium, constantly tossing the proton back and forth with the water, creating a gentle, balanced, and highly regulated acidity that is safe for the world. You already know this microscopic exchange of protons intimately through your own human senses. When you bite into a fresh, crisp slice of lemon or taste the sharp tang of vinegar, you are directly experiencing acidity. The sour receptors on your tongue are specifically designed to detect a high concentration of wandering hydrogen protons. Sourness is the literal taste of an acid. Conversely, bases are recognized by a bitter taste and a distinctively slippery feel. If you have ever touched wet baking soda or felt the slick, gliding surface of a bar of soap, you have felt a base. The The slippery feeling occurs because the base is gently reacting with the natural oils on your skin, turning them into microscopic amounts of soap right there on your fingertips. But the importance of acids and bases goes far beyond the foods we eat or the soaps we use. It is the invisible tightrope upon which your entire biological life balances. The blood flowing quietly through your veins right now must remain at a very specific, slightly basic pH of exactly 7.35 to 7.45. If the pH of your blood were to drift even slightly outside of this narrow window, the delicate proteins in your body would lose their shape and you would not survive. To prevent this, your body relies on magical mixtures called buffers. A buffer is a solution that uses the rules of Le Chatelier's principle from our last lesson to fiercely resist any change in pH. Your blood is filled with a mixture of weak acids and weak bases, acting as microscopic sponges. If a sudden flood of acidic protons enters your bloodstream, the weak bases immediately soak them up. If the blood becomes too basic, the weak acids gently release stored protons to replace the missing ones. Your blood constantly, actively adjusts itself, shifting left and right, back and forth, endlessly maintaining a state of perfect, quiet neutrality so that you may continue to breathe, rest, and heal. We have now watched the simplest piece of matter, the bare hydrogen proton, move gracefully from one molecule to another. We understand how the giving and taking of this single particle dictates the sour, the bitter, and the perfect buffered balance of the blood keeping you alive. We have seen what happens when atoms trade a proton. But what happens when they trade something even smaller and far more energetic? What happens when they trade the electron itself? As we drift peacefully toward our next lesson, we will leave the protons behind and follow the flowing stream of negative charge. When we return, we will uncover the invisible electric currents that power our modern world, diving into the sparking, energetic realm of oxidation reduction and electrochemistry. Rest deeply now, wrapped in the perfect, stable, and balanced chemistry of your own resting body. Lesson 1. Matter. Lesson 17. Oxidation reduction and electrochemistry. Welcome back, my friend, to the quiet stillness of our shared space. Once more, I invite you to settle deeply into the warmth and safety of your resting place. Close your eyes and take a long, slow breath in, filling your lungs with the cool, quiet air. Hold it for just a gentle moment and then release it, letting go of any lingering thoughts or tension from the waking world. In our last lesson together, we watched a beautifully simple exchange. We saw how molecules pass a single bare hydrogen proton back and forth, establishing the delicate, buffered balance of acids and bases that keeps our very blood flowing and neutral. We observed the trading of a positive charge. Tonight, we are going to look at the other side of that coin. What happens when atoms trade something even smaller and far more energetic? What happens when they trade their electrons? In this lesson, we will uncover the invisible electric currents that quietly power our modern world and our own beating hearts, as we dive into the sparking, energetic realm of oxidation reduction and electrochemistry. To understand this invisible current, we must return to the outer edges of the atom, to the swirling, restless clouds of electrons we explored at the very beginning of our journey. Throughout our lessons, we have seen atoms share these electrons to form bonds, seeking a state of quiet stability. But sometimes, the interaction is not a polite sharing. Sometimes, one atom has such a powerful magnetic pull that it completely strips an electron away from its neighbor, taking it entirely for itself. Chemists call this complete transfer of electrons an oxidation reduction reaction, though we usually just shorten it to a redox reaction. It is a dual process, two sides of the exact same coin, and one side cannot ever happen without the other. The first half of the process is called oxidation. Oxidation is the act of losing an electron. When an atom is oxidized, it is the generous donor, releasing a piece of its negative cloud out into the world. The second half of the process is called reduction. Reduction is the act of gaining that electron. The atom that is reduced is the welcoming receiver, catching the falling electron and pulling it tightly into its own orbit. It is important to remember that you cannot simply throw an electron away into empty space. An atom can only let go of its electron if there is another atom standing right there, waiting and ready to catch it. It is a perfectly matched, simultaneous exchange. One atom breathes out and the other breathes in. One lets go and the other takes hold. This silent, invisible handoff of negative charge is the fundamental heartbeat of electrochemistry. For a long time, this beautiful exchange simply happened in the dark. If you dropped a piece of zinc metal into a blue solution of copper, the zinc would instantly hand its electrons directly to the copper. The trade happened right where they touched, generating a tiny bit of heat, but nothing more. But then, scientists had a brilliant, world-changing realization. They realized that electricity itself is absolutely nothing more than the movement of electrons. If a redox reaction is simply the transfer of electrons from one atom to another, what would happen if we refused to let those atoms touch? What if we separated the generous donor and the welcoming receiver, placing them in two completely different glass beakers across the table from one another? If we connect those two beakers with a long, thin copper wire, the donor atom still deeply wants to give its electron away, and the receiver still desperately wants to pull it in. The magnetic desire remains. But now, the only way for the electron to make the journey is to travel all the way through the metal wire. As millions of electrons flow through that wire, traveling from the oxidation beaker to the reduction beaker, they create a steady, powerful stream of electrical current. By simply separating the two halves of the reaction, we tricked the chemical energy into becoming electrical energy. We created an electrochemical cell, more commonly known as a battery. But to keep this flow moving perfectly, nature requires her balance, just as we learned in our lesson on equilibrium. As all the negative electrons rush into the receiving beaker, that side becomes overwhelmingly negative, and the journey would quickly stall. To prevent this, scientists add a quiet, invisible connector called a salt bridge between the two beakers. The salt bridge gently leaks positive ions into the negative beaker, perfectly neutralizing the charge and maintaining the delicate harmony of the system, allowing the electrons to flow smoothly, continuously, and endlessly until the donor is entirely spent. This invisible, trapped waterfall of electrons is the very foundation of the modern era. Consider the device resting near you right now, gently playing the sound of my voice. Inside its sleek, silent casing lies a lithium-ion battery. There are no spinning gears or burning engines inside your phone. It is simply a carefully engineered box containing a redox reaction that has been cleverly separated. When you turn the screen on, you are opening a chemical gate. The lithium atoms on one side of the battery begin to oxidize, giving up their electrons. Those electrons are forced to travel through the complex circuitry of your phone, lighting up the screen and vibrating the speakers before finally arriving at the receiving atoms on the other side. You are harnessing the gentle, continuous flow of a microscopic chemical trade. But this elegant flow of charge is not limited to glass screens and metal wires. It is the exact mechanism keeping you alive as you rest. Deep inside every single one of your cells are tiny, magnificent structures called mitochondria. They are the powerhouses of your biology. When you eat a nourishing meal, the food is slowly and carefully oxidized. It gives up its electrons. Those electrons are passed down a highly controlled biological wire, a microscopic waterfall known as the electron transport chain. As the electrons flow gracefully down this chain, your body harvests their moving energy, using it to build the vital molecules that power your heartbeat, your breathing, and your dreams. At the very bottom of this waterfall, waiting patiently to catch the tumbling electrons, is the oxygen you just breathed in from the room. The oxygen is reduced, gracefully accepting the electrons and turning into pure, harmless water. Your entire existence is a slow, warm, and perfectly balanced electrical current. We have now watched the electron travel. We have harnessed its movement to light our homes, power our devices, and fuel the very cells of our bodies. Throughout our long journey together, we have focused almost entirely on these outer, swirling clouds of electrons. We have seen them shared, traded, gained, and lost. They dictate the shape, the phase, the speed, and the power of the chemical universe. But there is one place we have not yet explored. As we gently approach our final lesson together, we are going to look past the electron cloud entirely. We are going to dive straight into the incredibly dense, unimaginably powerful, and deeply mysterious heart of the atom itself. When we return, we will uncover the massive forces hidden within the center of matter, exploring the awe-inspiring realm of nuclear chemistry. Rest deeply now, feeling the quiet, steady, and warm electrical current of your own life gently humming within you. Lesson 1. Matter. Lesson 18. Nuclear Chemistry and the Heart of Matter. Welcome back, my friend, to the quiet stillness of our shared sanctuary, and to the very final chapter of our long and beautiful journey together. As we begin tonight, I invite you to settle yourself more deeply than ever before. Feel the soft, heavy comfort of your bed rising up to support you entirely. Close your eyes and take a slow, deep breath in, drawing the quiet night air deep into your lungs. Hold it there in the stillness, and then release it in a long, continuous sigh, letting every final trace of the waking world simply melt away. Over the course of our 17 previous lessons, we have marveled at the sweeping, intricate dance of the elements. We have watched molecules stretch and bend, we have seen them fly as gases and flow as liquids, and we have traced the invisible, sparking currents of their electrons. But throughout this entire journey, we have only been looking at the outer shell of reality. We have stayed safely in the swirling clouds of the electrons. Tonight, as we bring our grand exploration to a close, we are going to pierce that veil. We are going to leave the outer clouds behind and dive straight into the incredibly dense, unimaginably powerful, and deeply mysterious center of the atom itself. In this final lesson, we will uncover the massive forces hidden within the core of matter, exploring the awe-inspiring realm of nuclear chemistry. To truly grasp the nature of the atomic nucleus, we must first understand a profound paradox of scale and space. As we learned early on, an atom is composed almost entirely of empty space. If you were to expand a single atom until it was the size of a massive, echoing football stadium, the swirling electron cloud would reach all the way to the highest stadium seats. But the nucleus, the absolute center containing all the protons and all the neutrons, would be nothing more than a single, unimaginably dense marble resting quietly on the very center of the field. Even though it takes up almost zero space, that tiny marble contains over 99% of the entire mass of the atom. It is heavy, solid, and incredibly compact. But this extreme density presents a massive logical problem. We know from our studies that positive charges fiercely repel one another. The nucleus is packed tightly with positively charged protons, all shoved together into a microscopically small space. By the normal laws of electricity, those protons should violently push each other apart, instantly tearing the atom to shreds. The universe, by all logic, should simply fly apart. So, why does it stay together? It remains intact, because deep within that tiny marble, there exists a force unlike anything else we experience in our daily lives. Physicists call it the strong nuclear force. This force is the absolute strongest power in the known universe, but it comes with a strict condition. It only works at infinitesimally small distances. If protons are far apart, they repel each other. But if you can push them close enough together, if you can force them into that tiny, central marble, the strong nuclear force suddenly awakens, grabbing hold of the protons and neutrons with an unbreakable, binding grip that completely overpowers the electrical repulsion. It is this hidden, silent grip that holds the entire fabric of physical reality together. However, just like the delicate equilibria we studied in previous lessons, the nucleus is always seeking a perfect state of balance. The neutrons in the nucleus act as a sort of quiet buffer, providing extra strong nuclear force without adding any repulsive positive charge. But as atoms get larger and heavier, adding more and more protons, the tension inside the nucleus grows. The repulsive electrical force begins to push back against the strong nuclear force. Sometimes, the balance is lost, and the nucleus becomes unstable. When a nucleus finds itself in this restless, unstable state, it does exactly what every other chemical system in the universe does. It seeks peace. It seeks a lower, calmer energy state. To find this peace, the unstable nucleus will spontaneously exhale, throwing off tiny pieces of itself or releasing bursts of pure energy. We call this natural, balancing process radioactive decay. Radioactivity is often misunderstood as something inherently unnatural, but it is simply the atom finding its rest. Sometimes, the nucleus will eject a heavy chunk of 2 protons and 2 neutrons, known as an alpha particle, physically shrinking itself to become more stable. Other times, in a beautifully strange twist of quantum mechanics, a neutral neutron inside the core will suddenly transform itself into a positive proton, spitting out a negative electron in the process to balance the books. This is known as beta decay. And finally, as the newly shifted nucleus settles deeply into its new, comfortable arrangement, it often releases a soft, invisible sigh of pure light energy, known as a gamma ray. Through these quiet exhalations, something truly magical occurs. Because the atom has changed its number of protons, it is no longer the same element. It has literally transformed its identity. A restless atom of uranium can slowly, over billions of years, decay and transform into a perfectly stable, quiet atom of lead. This process is called transmutation. It is the ancient dream of the alchemists, happening silently and naturally in the rocks beneath our feet. A slow, geological clock ticking away the age of the Earth. This immense energy bound within the strong nuclear force is the very engine of the cosmos. While heavy elements seek peace by breaking apart a process called nuclear fission, the lightest elements seek peace by joining together. If you take 2 tiny, simple hydrogen nuclei and squeeze them together with enough immense pressure and blistering heat, the strong nuclear force will suddenly grab them, fusing them together to create a heavier atom of helium. This is called nuclear fusion. When those atoms fuse, a tiny fraction of their mass is not transferred. Instead, it is instantly converted into pure, radiant energy. This beautiful, violent merging of hydrogen is exactly what is happening right now in the deep, crushing core of our Sunday. Every ounce of warmth you have ever felt on your skin, every beam of light that has ever grown a green leaf on this planet, is the direct result of nuclear fusion happening millions of miles away. The light of the day is simply the energy released when tiny nuclei finally find their permanent embrace. But the story of the nucleus is also your own personal history. In the early moments of the universe, there was only hydrogen and a little bit of helium. There was no carbon, no oxygen, no iron, and no calcium. Every single heavy element required to build a human body was forged much later, in the blistering nuclear furnaces of ancient, dying stars. When those massive stars reached the end of their lives, they collapsed and exploded in magnificent supernovas, scattering their newly forged heavy nuclei across the empty void of space. Over billions of years, that scattered stardust drifted together to form our solar system, our planet, and eventually, you. The iron carrying oxygen in your blood, the calcium hardening your resting bones, and the carbon forming the very structure of your cells. All of it was born in the nuclear fire of a star that vanished billions of years ago. You are not just an observer of the chemical universe. You are made of its most ancient and profound history. And so, we have finally reached the end of our grand journey. We have traveled from the outermost edges of the electron cloud down to the absolute, fiery heart of matter itself. We have seen that the universe, in all its complexity, is simply a vast, interconnected system endlessly seeking balance, peace, and stability. Just as the restless atoms find their equilibrium, so too is it time for your mind and body to find theirs. There is nothing left to study, nothing left to solve, and nothing left to understand tonight. The universe will continue its quiet, perfect dance without you needing to watch it. You are made of stardust, held together by the gentle, invisible forces of nature, completely safe and completely whole. Allow the heavy, quiet peace of the solid world to hold you now. Drift away into the stillness and rest well, my friend. Sleep deeply and find your peace. Lesson 1. Matter